Imagine a place of perfect darkness, a silence so profound that it contains no echo, a void so complete that it holds no matter. For millennia, this was our image of space, our definition of nothingness. But this quiet emptiness is an illusion. It is the greatest secret of the cosmos, a secret that modern physics has only just begun to unveil. What we perceive as empty space is not empty at all. It is a seething, vibrant, and powerful quantum sea, an invisible ocean of energy that permeates every corner of the universe. This is the quantum vacuum, and it is the true foundation of our reality. It is a stage where the laws of our classical, intuitive world break down, and a stranger, more fundamental set of rules takes over. On this stage, particles can be in multiple places at once. They can be connected across vast, cosmic distances in an instant. They can tunnel through barriers that should be impenetrable. This is a reality where the very act of looking at something changes what is there. The quantum vacuum is not a passive backdrop. It is an active, creative medium, a silent but powerful engine that shapes the destiny of the universe. It is a place where matter, energy, and even time itself are born from the incessant, ghostly dance of quantum fields. Today, we will step behind the curtain of classical reality. We will part the veil of the visible, and we will journey into the heart of this mysterious, invisible realm. We will explore the paradoxes, the puzzles, and the profound philosophical implications of a universe where the most potent force may be the energy of emptiness itself. This is a journey that will challenge your perceptions, your assumptions, and your very understanding of what it means to exist. Because in the quantum world, reality is far stranger, more flexible, and more beautiful than you can possibly imagine. One of the first and most unsettling signposts on the road into this quantum territory is a thought experiment involving a cat, a box, and a single, unpredictable atom. It is the story of Schrödinger's cat, a parable designed not to describe a real experiment, but to expose the jarring and seemingly absurd consequences of applying the laws of quantum mechanics to the macroscopic world we inhabit. Inside a sealed box, a cat's life hangs in the balance, its fate linked to the decay of a single radioactive atom. If the atom decays, a mechanism is triggered, a vial of poison is shattered, and the cat dies. If the atom does not decay, the cat lives on. From our classical perspective, the situation is simple. The cat is either alive or dead. We just don't know which until we open the box. But quantum mechanics offers a far more radical and disturbing picture. A radioactive atom, until it is measured, exists in a state of superposition. It has both decayed and not decayed at the same time. And because the cat's fate is quantum mechanically entangled with the atoms, the cat itself must also be in a superposition of states. It is, in the bizarre and unsettling language of the quantum world, simultaneously alive and dead, a ghostly amalgamation of two mutually exclusive realities, coexisting within the unobserved confines of the box. This is not a statement about our ignorance. It is a statement about the fundamental nature of unobserved reality. The cat's reality is not a single definite state, but a wave function, a cloud of probabilities. The moment we open the box, the moment our observation interacts with the system, this wave function collapses. The superposition is broken, and a single definite reality is chosen from the menu of possibilities. The cat is either alive or it is dead. The act of looking seems to have forced the universe to make up its mind. This measurement problem is the deep, unresolved wound at the heart of quantum mechanics. It raises profound questions about the nature of reality and the role of the observer. Does the world have definite properties when we are not looking? Or does the act of observation itself bring the world into being? Schrödinger's cat is a macroscopic amplifier of this quantum weirdness, a bridge from the abstract world of particles to the concrete world of our experience. It is a metaphor for the inherent uncertainty and potentiality that underlies all of existence. We are all, in a sense, living in Schrödinger's box, our own futures existing as a superposition of all possible outcomes until the moment of now collapses the wave function of our own lives. And as we drift into the liminal space of sleep, our own consciousness enters a state akin to that of the unobserved cat. The definite classical reality of the waking world fades, and we are suspended in a superposition of memories, thoughts, and dreams, a state where life and death, past and future, self and other, can coexist in a fluid, paradoxical, and deeply creative dance. The bizarre state of Schrödinger's cat is a direct consequence of the principle of quantum superposition, a cornerstone of the quantum worldview that shatters our classical intuition about how things exist in the world. In our everyday experience, an object has a single, definite set of properties. A ball is here, not there. A car is red, not blue. But at the fundamental, subatomic level, the rules are different. A quantum particle, like an electron, is not a solid, point-like object. It is better described as a probability wave, a diffuse cloud of potential that is spread out over a region of space. Before it is measured, it does not have a definite position. It exists in a superposition of all possible positions. It is, in a very real sense, in many places at once. The most striking and famous demonstration of this is the double-slit experiment, when a beam of electrons is fired at a barrier with two parallel slits, and we do not try to determine which slit each electron passes through. An interference pattern appears on a detector screen behind the barrier. This pattern of alternating bright and dark bands is the classic signature of waves interfering with each other, like the ripples from two stones dropped in a pond. This happens even if the electrons are fired one at a time. Each individual electron seems to pass through both slits simultaneously, as a wave, and then interfere with itself. It is a mind-bending result that suggests that the electron's reality is not localized until it is forced to be. The moment we place a detector at one of the slits to watch which path the electron takes, the wave-like behavior vanishes. The interference pattern disappears, and we see two simple bands on the screen, corresponding to the two slits. The electron now behaves like a well-behaved particle, choosing one path or the other. The act of measurement, of gaining which path information, has collapsed the superposition and forced the electron to adopt a single, definite reality. Superposition is not just a theoretical curiosity, it is the engine of quantum technologies. A classical computer bit is binary. It can be either a 0 or a 1. A quantum bit, or qubit, can be in a superposition of both 0 and 1 at the same time by linking many qubits together. A quantum computer can explore a vast computational space simultaneously, giving it the potential to solve problems that are far beyond the reach of any classical machine. But the implications of superposition extend beyond technology and into the very fabric of our subjective experience. The state of our own mind often resembles a superposition. We can hold contradictory feelings at the same time, love and frustration, hope and fear. Our identity is not a single, fixed thing, but a superposition of our various roles, memories, and potential selves. And in the state of sleep, this mental superposition becomes the dominant reality. The linear, logical, and collapsed state of waking consciousness gives way to the fluid, associative, and superpositional nature of the dream world. In a dream, we can be both the protagonist and an observer. We can be in our childhood home and a futuristic city at the same time. The rigid either-or logic of the classical world is replaced by the inclusive both-and logic of the quantum realm. Superposition is the universe's way of telling us that reality, at its core, is not a collection of fixed facts, but a vibrant, dynamic, and multi-layered web of possibilities. And every night, as we surrender to sleep, we are given the chance to immerse ourselves in this fundamental, creative, and endlessly mysterious aspect of our own being. The transition from the probabilistic, superpositional world of quantum potential to the definite, singular world of classical reality is the central mystery of the quantum measurement problem. The wave function is the mathematical description of a quantum system's superposition, a complete catalog of all its possibilities and their associated probabilities. As long as the system is isolated, its wave function evolves in a smooth, continuous, and perfectly deterministic way, governed by the elegant Schrödinger equation. But the moment a measurement occurs, this smooth evolution is violently interrupted. The wave function is said to collapse, and from the vast menu of possibilities, a single random outcome is actualized. This collapse is not part of the Schrödinger equation. It is a separate, mysterious process that we have to add to the theory to make it work. But what, precisely, constitutes a measurement? Is it the interaction with a large classical measuring device? Is it the irreversible recording of information, or does it require the intervention of a conscious observer? This is the question that has spawned a century of debate and a zoo of different interpretations of quantum mechanics. The traditional Copenhagen interpretation, championed by Niels Bohr, takes a pragmatic but philosophically unsatisfying stance. It simply posits a fundamental divide, a shifty split, between the quantum world of microscopic systems and the classical world of our measuring apparatus. When these two worlds interact, a collapse occurs. The theory does not explain the mechanism of this collapse. It treats it as a primitive, unexplained feature of nature. This reluctance to address the how of the collapse led many physicists to seek alternatives. The many worlds interpretation of Hugh Everett III offers a breathtakingly bold solution. The collapse never happens. The wave function is the complete description of reality, and its smooth evolution is the only process that ever occurs. When a measurement is made, the universe itself branches into multiple, parallel realities, one for each possible outcome. In one world, the electron goes through the left slit. In another, it goes through the right. The observer also splits, with different versions of the observer experiencing different outcomes. In this view, reality is a constantly branching tree of possibilities, and we are just following one particular path through this vast multiverse. There is no special measurement process, no mysterious collapse, only the universal, deterministic evolution of the wave function of the whole cosmos. A different approach is taken by objective collapse theories. These models propose that the collapse is a real, physical process that happens spontaneously, independent of any observer. The collapse is a random, probabilistic event, and its likelihood depends on the size and complexity of the system. For a single, isolated particle, the chance of a spontaneous collapse is infinitesimally small, so it can maintain its superposition for a long time. But for a macroscopic object like a cat or a measuring device, which consists of trillions upon trillions of entangled particles, the probability of a collapse occurring in one of its constituent particles becomes overwhelmingly high, triggering a rapid chain reaction collapse of the entire system. This is why we never see macroscopic superpositions. They are simply too fragile, collapsing into a definite state in an immeasurably short time. The measurement problem remains the most profound conceptual challenge in modern physics. It is the point where our theories of the physical world seem to touch upon the nature of information, reality, and perhaps even consciousness itself. And it is a problem that finds a powerful experiential parallel in the nightly journey of our own minds. As we fall asleep, the constant bombardment of sensory information from the external world, the stream of measurements that keeps our waking consciousness collapsed into a single, coherent reality, begins to cease. The neural gateways to the environment close, and our consciousness is released from its classical constraints. It enters a state of pure, uncollapsed potential, a state of superposition where memories, emotions, and possibilities can float and merge freely. Sleep is a nightly, voluntary retreat from the tyranny of the collapsed wave function, a journey back into the fertile, probabilistic sea from which all realities are born. The quantum world is not just a world of possibility, it is also a world of fundamental limits, a world where the very act of knowing changes what can be known. This is the essence of Werner Heisenberg's uncertainty principle, one of the most elegant, profound, and misunderstood concepts in all of science. It is not a statement about the clumsiness of our measuring instruments. It is a deep, intrinsic, and unavoidable feature of the wave-like nature of reality. The principle states that there are certain pairs of properties of a quantum system that are complementary the more precisely you know one, the less precisely you can know the other. The classic example is position and momentum. An object's momentum is a measure of its motion, its mass times its velocity. To have a well-defined momentum, a particle must have a well-defined wavelength, but a wave with a single, precise wavelength, like a pure musical note, is by its very nature spread out over all of space. It does not have a precise position. Conversely, to have a precise position, a particle's wave function must be squeezed into a very narrow spike. But a spike like this is a superposition of a huge number of different wavelengths, meaning its momentum is highly uncertain. You can know where it is, or you can know where it is going, but you can never, even in principle, know both with perfect precision. This is not a failure of our technology. It is a fundamental law of the cosmos. This principle has far-reaching consequences. It is the reason for the stability of atoms, preventing electrons from collapsing into the nucleus. It is the source of the zero-point energy of the vacuum, the irreducible quantum jiggle that ensures nothing can ever be truly at rest. And it is a powerful metaphor for the nature of our own consciousness and our search for knowledge. Our minds, too, operate under a kind of uncertainty principle. We can focus our attention with laser-like precision on a single detail, a single fact, a single aspect of a problem. But in doing so, we inevitably lose sight of the broader context, the interconnectedness, the bigger picture. Our knowledge of the position of the fact becomes precise, but our knowledge of its momentum, its meaning, and its relationship to the whole becomes uncertain. Conversely, we can adopt a broad, holistic perspective, seeing the interconnected patterns and the flow of the whole system. But in doing so, we lose the sharp focus on the individual details. There is a fundamental trade-off between focused analysis and holistic synthesis. As we prepare for sleep, we experience this mental uncertainty in a very direct way. The focused, goal-oriented mind of the waking state, with its constant attempts to control, to plan, and to know with certainty, begins to relax. We surrender to the gentle, associative flow of hypnagogic thought. The sharp boundaries between ideas blur. The distinction between memory and imagination fades. We enter a realm where knowledge is not about certainty, but about possibility. In the dream state, this uncertainty becomes the very fabric of reality. The world of the dream is not governed by the fixed laws of classical causality, but by the fluid, associative logic of the unconscious. It is a world where anything is possible, where the normal constraints of identity, time, and space are lifted. This is not a state of confusion. It is a state of profound creative freedom. It is in this state of uncertainty that the mind can make new connections, generate new insights, and heal old wounds. The uncertainty principle, then, is not a pessimistic limit on our knowledge, but a cosmic guarantee of freedom and creativity. It ensures that the universe and our own laws will never be fully predictable, fully controllable, fully known. It ensures that there will always be room for surprise, for novelty, for the emergence of the unexpected, and every night, as we surrender to the peaceful uncertainty of sleep, we are aligning ourselves with this fundamental, creative, and liberating principle of the cosmos. The strange and beautiful phenomenon of quantum entanglement is a direct and powerful testament to the holistic and non-local nature of the universe. It is a connection between two or more particles that is so intimate and profound that it defies our classical intuition about space, distance, and separateness. When particles are created or interact in a specific quantum mechanical way, their individual wave functions can become merged into a single, unified wave function that describes the entire system. From that moment on, they are no longer independent entities, but are two aspects of a single, indivisible whole, even if they are subsequently separated by vast cosmic distances. The classic example involves a pair of entangled photons. If they are created in such a way that their total spin is zero, then we know that if one photon is measured to have spin up, its partner, no matter how far away, must instantly be found to have spin down. The strangeness lies in the fact that, according to quantum mechanics, neither photon has a definite spin until it is measured. Each exists in a superposition of both spin up and spin down. It is only the act of measuring one that collapses the wave function of the entire entangled system, instantly determining the state of the other. This spooky action at a distance, as Einstein called it, seems to imply a form of communication that is faster than the speed of light, a violation of one of the most fundamental principles of physics. However, numerous experiments have confirmed that this is not the case. While the correlation between the measurement outcomes is instantaneous, it cannot be used to transmit information in a controllable way. The outcome of the first measurement is fundamentally random. You cannot decide in advance whether you will get spin up or spin down, and therefore you cannot use this to send a deliberate message. But the underlying, instantaneous connection is undeniably real. It tells us that our notion of a universe made up of separate, independent objects is an illusion, an approximation that works well in our macroscopic world, but breaks down at the fundamental level. At its core, the universe is not a collection of things. It is a network of relationships. This has profound philosophical and even spiritual implications. It suggests that the sense of separation we feel as individual beings is not the ultimate reality. We are all, in a very real physical sense, entangled with each other and with the cosmos as a whole. The atoms in our bodies were forged in the hearts of stars that died billions of years ago, their remnants scattered across the galaxy and eventually coalescing to form our sun, our planet, and ourselves. We are physically connected to the history of the universe, and perhaps, through the quantum nature of our own consciousness, we are also entangled in a more immediate, non-local way. The feeling of deep empathy, the sense of connection that can span vast distances, the collective consciousness that can emerge in groups, these are all experiences that hint at a reality beyond our individual, isolated selves. Sleep is a state where we may be particularly receptive to these entangled connections, as the ego, the fortress of our individual identity, lowers its drawbridge. Our consciousness can become more open to the subtle, non-local currents of the universal quantum field. In dreams, our sense of a separate self often dissolves. We can merge with other people. We can experience events from a collective perspective. We can feel a deep sense of unity with the natural world. These are not just psychological fantasies. They may be the subjective experience of the fundamental, entangled nature of reality. They are moments when our individual wave function remembers its connection to the universal wave function. Entanglement is the universe's most profound secret, a secret that tells us that despite the vast, cold distances of space, nothing is truly separate. We are all part of a single, vast, and mysterious quantum dance, and in the quiet, boundaryless realm of sleep, we are invited to join in, to feel the rhythm of our own connection, and to remember the deep and beautiful truth of our own inseparable unity. The thought experiment of Schrödinger's cat, with its absurd and paradoxical imagery, has become an enduring cultural touchstone, a symbol of the profound weirdness that lies at the heart of the quantum world. But its importance goes far beyond its role as a clever metaphor. It is a powerful conceptual tool that forces us to confront the deepest and most uncomfortable questions about the nature of reality. The cat in the box, suspended in its ghostly state between life and death, is a direct challenge to the philosophical position of naive realism. The common sense idea that the world is exactly as it appears, and that objects have definite properties whether we are looking at them or not. Quantum mechanics suggests that this is not the case. At the fundamental level, reality is a realm of potential, of probability, of superposition. The definite, classical world we experience is not the fundamental reality. It is a collapsed reality, a reality that has been actualized from a sea of possibilities through the act of interaction and measurement. This raises the question of where the cut between the quantum and classical worlds lies. At what point does a system stop behaving quantum mechanically and start behaving classically? Is it a matter of size, of complexity, of temperature, of interaction with the environment? This is the problem of decoherence, a central topic in modern quantum physics. Decoherence theory suggests that a quantum system, like our atom, rapidly loses its superpositional nature when it becomes entangled with its environment. The information about its superposition leaks out into the vast number of degrees of freedom of the surrounding world, the air molecules in the box, the photons of light, the cat itself, making it practically impossible to ever detect the superposition directly. In this view, the cat is never really both alive and dead. Its macroscopic nature means it is so strongly entangled with its environment that its wave function collapses into a definite state in an immeasurably short time, long before we ever open the box. The collapse is not caused by the conscious observer, but by the unavoidable process of environmental entanglement. This provides a pragmatic and physically plausible solution to the paradox, but it does not fully solve the measurement problem. It explains why we do not see macroscopic superpositions, but it does not explain which definite outcome is chosen from the initial superposition, or why. It pushes the mystery of the collapse from the act of measurement to the process of decoherence. But the fundamental question remains. This ongoing debate has a powerful resonance in our own search for self-understanding. Our own consciousness can be seen as a system that is constantly navigating the line between quantum-like potential and classical-like actuality. Our inner world is a realm of superposition of conflicting desires, of unresolved emotions, of potential life paths. This is the realm of the unconscious. Our waking, conscious mind, however, is a collapsing agent. It is constantly making choices, forming beliefs, creating a coherent narrative of who we are. It is collapsing the vast, superpositional potential of our psyche into a single, definite, classical self. But this classical self is always, to some extent, an illusion, a simplification. The underlying quantum potential is still there, and it often surfaces in our dreams, in our slips of the tongue, in our moments of creative insight. The process of psychotherapy, in many ways, is a process of consciously re-engaging with this uncollapsed superpositional aspect of ourselves. It is about opening the sealed boxes of our own past, of facing the inner Schrodinger's cats of our traumas and our disowned desires, and in doing so, allowing for a new, more integrated collapse to occur. Sleep is the natural, nightly laboratory for this kind of psychic work. It is a time when the classical, collapsing ego is put on hold, and the quantum, superpositional unconscious is allowed to come to the fore. In the bizarre symbolic language of our dreams, we are given a chance to dance with our own possibilities, to confront our own paradoxes, and to glimpse the deep, strange, and beautiful quantum reality that lies at the heart of our own being. The phenomenon of quantum tunneling, the ability of a particle to pass through a classically forbidden barrier, is a stunning testament to the wave-like nature of reality and the probabilistic heart of the universe. It is a process that is both deeply mysterious and utterly essential to our existence. The sun shines, our digital technologies function, and the very elements that make up our bodies were forged in the hearts of stars, all thanks to this strange quantum leap. But quantum tunneling is not just a physical process. It is a powerful metaphor for transformation, for breakthrough, for the emergence of the new and the unexpected. It tells us that the barriers we perceive in our own lives, whether they are physical, emotional, or psychological, are not as solid and absolute as they may seem. Our classical, logical mind often sees the world in terms of impenetrable walls. We do not have enough money, enough time, enough talent. We are too old, too young, too broken. These are the energy barriers of our own psyche. And if we approach them with a purely classical, particle-like mindset, we will simply bounce off of them, our limiting beliefs confirmed. But if we can learn to access our own inner wave nature, the story changes. The wave-like aspect of our consciousness, our creativity, our intuition, our capacity for associative thinking, our ability to see a problem from a completely new perspective is not stopped by barriers. It can, in a sense, leak through them. A solution to a problem that seemed impossible can suddenly appear in a flash of insight. A deeply ingrained emotional pattern can suddenly release its grip. A new path forward can open up where before there was only a solid wall. This is the experience of mental tunneling. And it is an experience that is most accessible to us when we are not trying too hard, when we are not in a focused, particle-like state of mind. It often happens in the shower, on a long walk in nature, in the midst of a creative activity, or, most profoundly, during sleep. Sleep is the ultimate incubator for quantum tunneling. As the conscious problem-solving mind rests, the unconscious is free to explore the vast, interconnected web of our neural networks. It can make connections, try out new combinations, and test out new pathways that are not constrained by the rules of logic. It can tunnel through the mental blocks and the emotional barriers that have kept us stuck. This is why we can often go to sleep with a seemingly intractable problem and wake up in the morning with a clear solution, or at least a new perspective. The unconscious has done the work for us, not by breaking down the wall, but by finding a way through it. The story of quantum tunneling is a message of profound hope and possibility. It is the universe's way of reminding us that we are not trapped by our current circumstances or our past conditioning. We are probabilistic, wave-like beings, with a built-in capacity for breakthrough and transformation. It is an invitation to trust in the creative intelligence of our own unconscious, to honor the wisdom of our own sleep, and to know that even when we are faced with what seems like an insurmountable wall, there is always a chance, however small, of a miracle. There is always a possibility of tunneling through to the other side. The principle of superposition is a declaration that reality, at its core, is a realm of radical multiplicity. The universe is not a single fixed story. It is a library containing an infinite number of possible stories, and our lived experience is just one volume that we have chosen to read. This is a concept that can be both exhilarating and overwhelming. It is exhilarating because it speaks to a universe of infinite creative potential. It is overwhelming because it challenges our deep-seated need for certainty, for a single, stable, and reliable reality. But this multiplicity is not just a feature of the subatomic world. It is a defining characteristic of our own human experience. We are not single, unified selves. We are a complex, dynamic, and often contradictory superposition of different identities, different desires, and different life narratives. The psychoanalyst Carl Jung spoke of the archetypes of the collective unconscious, the hero, the trickster, the wise old man, the great mother as fundamental patterns of human potential that exist within all of us. The psychologist Roberto Assagioli developed a model of the psyche called psychosynthesis, which sees the self as a symphony of different subpersonalities, each with its own voice, its own needs, and its own perspective. We are a committee, a cast of characters, an internal ecosystem. In our waking lives, we often identify with only one or two of these subpersonalities: the responsible adult, the ambitious professional, the dutiful parent. The other parts of ourselves, the playful child, the wild artist, the contemplative mystic, are often suppressed, judged, or ignored. They are relegated to the unconscious, the uncollapsed superposition of our own being. But they do not go away. They continue to exist as a latent potential, and they often make their presence known in our dreams. Sleep is the great theater of our inner multiplicity. In the dream state, the dominant, waking ego steps aside, and all the other characters in our inner drama are given a chance to take the stage. We can have a dream where we are a courageous hero, facing down a terrible monster, only to have another dream the same night where we are a helpless victim, fleeing in terror. We can dream of ourselves as a wise sage, dispensing profound advice, and then as a foolish trickster, playing pranks and causing chaos. These are not just random, meaningless images. They are the voice of our unlived lives, the expression of our uncollapsed potential. The dream is the psyche's way of maintaining its wholeness, of reminding us that we are more than just the limited, partial identity we present to the world. It is a nightly invitation to embrace our own inner diversity, to honor all the different parts of ourselves, even the ones we find difficult or shameful. The process of becoming a whole, integrated human being is not about choosing one true self and rejecting all the others. It is about becoming a wise and compassionate conductor of our own inner orchestra, a person who can allow all the different instruments to play their part in the beautiful, complex, and sometimes dissonant symphony of our own being. Superposition is not a problem to be solved. It is a gift to be celebrated. It is the source of our richness, our complexity, and our infinite capacity for growth and transformation. And every night, in the deep, multiplicitous world of our dreams, we are given the chance to remember and to reclaim this fundamental quantum truth of who we really are. The decay of a radioactive atom is a quantum event that is both profoundly simple and deeply mysterious. It is simple in that it is a binary process. The atom is either in its initial, unstable state, or it has decayed into a new, more stable state. It is mysterious in that the timing of this event is fundamentally irreducibly random. This randomness at the heart of nature is a deep challenge to the classical, deterministic worldview, which held that if we knew the precise state of the universe at one moment, we could, in principle, predict its entire future. Quantum mechanics tells us that this is not possible. The universe has a built-in, intrinsic spontaneity, but this spontaneity is not just a feature of the physical world. It is also a powerful metaphor for the nature of change and transformation in our own lives. We often think of personal growth as a slow, linear, and cumulative process. We read the books, we do the work, we make the incremental changes, but very often, the most profound shifts in our lives do not happen this way. They happen in a moment, a sudden insight, a flash of intuition, a moment of grace, a peak experience. These are the decay events of the psyche. They are moments when a long-held, unstable emotional or cognitive structure suddenly collapses, and we are transformed into a new, more integrated state of being. These moments are often unpredictable. They can come in the midst of a deep crisis or in a moment of quiet contemplation, but they are always transformative. And just as the decay of an atom releases energy, these moments of psychic decay release a tremendous amount of psychic energy, energy that was previously bound up in maintaining our old defensive structures. This is the energy of liberation, of joy, of creative flow. Sleep and dreams are a particularly fertile ground for these kinds of spontaneous transformations. The dream state is a realm of heightened emotional intensity and fluid, associative thinking. It is a state where the normal, linear, and logical constraints of the waking mind are relaxed. This can create the perfect conditions for a quantum leap in our understanding. A recurring nightmare, which represents a stuck, unstable emotional state, can suddenly transform into a dream of resolution and healing. A symbol that has been haunting our dreams for weeks can suddenly reveal its meaning in a flash of insight. We can wake up in the morning feeling fundamentally different, as if a great weight has been lifted, without being able to point to a specific logical cause. This is the magic of unconscious processing, the mind's own innate capacity for spontaneous self-healing and transformation. The law of radioactive decay is not a law of death. It is a law of change. It is the universe's way of ensuring that nothing stays stuck forever. It is a promise that even the most stable, rigid, and seemingly intractable patterns, both in the physical world and in our own psyches, are ultimately subject to the possibility of a sudden, unpredictable, and liberating transformation. It is a reminder to trust in the spontaneous, creative intelligence of the universe and of our own deep selves, an intelligence that is always at work, both in the light of day and in the dark. Mysterious and transformative crucible of our dreams, the wave-particle duality, the central paradox of the quantum world, is not a problem to be solved, but a deep, generative tension to be lived. It is the cosmic dance between the potential and the actual, the unmanifest and the manifest, the one and the many. This is a dance that is not just happening in the subatomic realm. It is happening at every level of our own being. Our lives are a constant oscillation between our wave-like nature and our particle-like nature. The wave is our connection to the infinite, the unformed, the realm of pure potential. It is our capacity for imagination, for intuition, for empathy, for a sense of unity with all of life. It is the part of us that dreams, that creates, that loves unconditionally. The particle is our connection to the finite, the formed, the realm of the actual. It is our capacity for focused action, for logical thought, for making distinctions, for navigating the practical world of time, space, and matter. It is the part of us that builds, that achieves, that creates a unique, individual life. A healthy, integrated life requires a dynamic balance between these two modes. If we live too much in the wave, we can become ungrounded, lost in fantasy, unable to bring our dreams and visions into the concrete reality of the world. If we live too much in the particle, we can become rigid, disconnected, cut off from the source of our own creativity and from our sense of connection to the larger whole. We become a thing in a world of things, a cog in a machine. The modern world, with its emphasis on productivity, on efficiency, on the quantifiable, on the individual, has a strong bias towards the particle nature of our being. We are encouraged to be focused, to be definite, to be certain. The wave-like aspects of our nature, our intuition, our creativity, our need for unstructured time, for connection, for simply being are often devalued, dismissed as impractical or unproductive. This creates a deep imbalance, both in our individual psyches and in our collective culture, and sleep is the great, nightly corrective to this imbalance. Sleep is the time when the particle-like ego dissolves and we are re-immersed in the deep, generative, wave-like ocean of the unconscious. It is a time for the other side of our nature to have its voice, to be seen, to be honored. In our dreams, we are not particles, but waves. We flow, we merge, we transform. The rigid categories of the waking world dissolve. The forgotten parts of ourselves are remembered. The connections we have lost are re-established. To sleep is to restore our wholeness, to rebalance the fundamental duality of our own being. It is to remember that we are not just the finite, separate, and mortal individuals we appear to be in the light of day. We are also, and just as truly, infinite, interconnected, and eternal waves in the vast, mysterious, and beautiful ocean of the cosmos. To understand the wave-particle duality is to understand the very rhythm of life, and to honor our sleep is to honor our sacred and essential place within that cosmic dance. The law of radioactive decay, with its inherent element of chance, offers a profound insight into the nature of time's arrow. We experience time as a relentless, unidirectional flow, a one-way street from the past to the future. The second law of thermodynamics provides the physical underpinning for this, stating that the overall entropy, or disorder of the universe, always increases. But quantum mechanics adds a crucial layer of subtlety to this picture. The decay of a single atom is an irreversible event. Once the atom has decayed, it cannot undecay. This process creates a distinction between the past and the future, a moment of irreversible change that contributes to the overall arrow of time. However, the timing of this event is not deterministic. The universe at its core seems to have a built-in element of spontaneity, of creative unpredictability. Time's arrow is not just the result of a slow, steady increase in disorder. It is also punctuated by these random, information-creating, quantum events. This suggests a picture of time that is not a smooth, featureless river, but a dynamic, unfolding process, a story that is being written, moment by moment, through the resolution of quantum possibility. This has a powerful parallel in our own subjective experience of time and personal growth. Our lives are not a smooth, predictable unfolding of a pre-written script. They are a series of moments, of choices, of decay events that shape our path, a sudden insight, a change of heart, a decision to leave a job or a relationship. These are the moments that define the arrow of our own personal time. They are moments of irreversible change, moments when the superposition of our own potential collapses into a single, definite path. And often, these moments are not the result of a long, logical deliberation. They can feel spontaneous, intuitive, almost random, a quantum leap of the soul. Sleep is a realm where we are particularly close to this creative, spontaneous nature of time. In the dream state, the mind is not bound by the linear, causal logic of the waking world. It can play with time. It can rehearse different potential futures. It can reprocess the decay events of the past. A dream can take a painful memory and reframe it, allowing for a new kind of decay, a decay of the old, painful emotional charge, and a transformation into a new, more integrated understanding. This is the healing power of dreams, their ability to work with the arrow of our own personal time, to help us let go of the past and to open up to the new possibilities of the future. The quantum nature of decay, then, is not just a curiosity of physics. It is a deep metaphor for the process of life itself. It tells us that the universe is not a static, predetermined machine, but a dynamic, creative, and constantly unfolding story. And we are not just passive observers of this story. We are active participants, co-creators of our own personal arrow of time, shaping our destiny, moment by moment, through the choices we make, the insights we have, and the deep, transformative work we do in the silent, timeless, and sacred space of our own sleep. The quantum principle of superposition, the idea that a particle can exist in multiple states at once, is not just a statement about the physical world. It is a profound revelation about the nature of the soul. Our classical, Western model of the self is that of a single, unified, and coherent entity. But our own direct experience, especially in moments of introspection and in our dreams, often tells a different story. We are a multiplicity, a chorus of different voices, a superposition of different selves. The confident self, the insecure self, the compassionate self, the angry self, the child, the elder. All of these and more coexist within the quantum field of our own psyche. This is not a sign of pathology. It is the very nature of our richness and complexity. In our waking lives, we often collapse this rich superposition into a single, socially acceptable persona. We present a single, coherent face to the world, but this is always a partial truth, a single collapsed state from an infinite sea of possibilities. The other selves, the other potentials, are not destroyed. They are simply relegated to the unconscious, where they continue to exist in a state of superposition. And it is in our sleep, in the theater of our dreams, that these other selves are given a voice, a stage, a chance to be seen and heard. A dream is a journey into the superposition of the soul. We can dream of ourselves as a powerful monarch, and in doing so we are touching the archetypal energy of the king or queen within us, our capacity for sovereignty, for responsibility, for just and wise leadership. We can dream of ourselves as a frightened, abandoned child, and in doing so, we are connecting with the vulnerable, wounded part of our own being that needs care and compassion. We can dream of ourselves as a wild animal, and in doing so we are accessing our own instinctual, untamed nature. These dream figures are not just random symbols. They are aspects of our own multiplicitous being. They are the other yous that make up the full superposition of who you are. To work with our dreams, to pay attention to them, to honor them, is to engage in a process of psychic integration. It is to become more aware of the different voices within our own internal chorus, and to learn to become a more compassionate and inclusive conductor of our own inner symphony. This is a process that leads to a greater sense of wholeness, of authenticity, of creative power. It is the process of moving from a collapsed, partial self to a more fluid, dynamic, and superpositional self. A self that can consciously embrace and integrate its own inner multiplicity. The quantum world tells us that reality is not a single, fixed thing, but a vibrant, multi-layered, and superpositional dance of possibility. And our own souls are no different. We are not single notes, but rich, complex chords. And our dreams are the music we make in the silent, sacred, and superpositional space of the night. The observer effect in quantum mechanics is a profound and unsettling revelation that blurs the line between the subjective and the objective, between the mind and the world. It tells us that the universe is not a detached, independent reality that we passively perceive. It is a participatory cosmos, a reality that responds to, and is shaped by, the very act of our observation. When we are not looking, a quantum system exists as a wave of potential. When we look, it collapses into a particle of actuality. Our gaze, our awareness, is not a neutral act. It is a creative world-shaping force. This is a concept that has deep and powerful implications for our own lives and our own power to shape our reality. The world we experience is not an objective out there. It is a mirror, reflecting back to us the quality of our own attention, the nature of our own consciousness. If we approach the world with a mindset of criticism, of judgment, of fear, we will tend to selectively perceive and amplify the evidence that confirms this worldview. The world will, in a sense, collapse into a state that matches our observation. The people we meet will seem more hostile. The challenges we face will seem more insurmountable. The beauty of the world will be obscured. If, on the other hand, we can cultivate a gaze of compassion, of curiosity, of appreciation, the world will respond in kind. We will start to notice the small acts of kindness, the hidden beauty in the everyday, the opportunities for connection and growth that were always there, but were previously unobserved. Our observation does not create the world out of nothing, but it does collapse the vast, superpositional potential of the world into a particular, experienced reality. We are the artists of our own perception, and this creative act of observation is not limited to our waking lives. Sleep is a time when the observer turns inward. The lens of our consciousness, which is usually directed at the external world, turns to face the vast, inner landscape of our own psyche. And in our dreams, we are both the artist and the canvas, the observer and the observed. The world of the dream is a direct and unfiltered manifestation of our own inner state. The characters we meet are projections of our own subpersonalities. The landscapes we traverse are maps of our own emotional terrain. The narratives that unfold are the stories of our own deepest conflicts and aspirations. And the way we interact with this dream world, the way we observe it from within, has a powerful effect on its evolution. If we run from the monster in our dream, it will likely grow larger and more terrifying. If we can find the courage to turn and face it, to ask it what it wants, it can often transform, revealing itself to be a source of hidden strength or a messenger of some forgotten truth. This is the observer effect at play in the laboratory of the soul. It is the recognition that our awareness is not a passive witness, but an active, transformative force. To become a more conscious dreamer, to bring a quality of lucid awareness to our sleep, is to practice this creative art of observation in its purest form. It is to learn to consciously and intentionally shape the reality of our own inner world, a skill that can then be brought back into the waking state. The observer effect is not just a strange quirk of physics, it is a sacred responsibility. It is a call to become more conscious of our own gaze, to recognize its power, and to learn to look at ourselves, at each other, and at the world with a quality of attention that is worthy of the beautiful, mysterious, and participatory cosmos we inhabit. The wave function, the central mathematical object of quantum mechanics, is more than just a tool for calculating probabilities. It is a poetic and powerful map of the hidden, potential nature of reality. It tells us that the universe, at its core, is not a world of solid, definite things, but a shimmering, vibrant sea of possibility. A particle is not a point, it is a wave of potential, spread out in space, containing the possibility of being found here, or there, or anywhere in between. The wave function is the mathematical description of this field of potential. It is the score for the cosmic symphony, a symphony where the notes are not fixed, but are a superposition of all possible tones, waiting to be played. This is a vision of reality that is deeply resonant with our own subjective experience of life. Our lives, too, are a wave function. Our future is not a single predetermined path, but a superposition of all possible futures. Every moment is a crossroads, a point where the wave function of our life can collapse into a new, definite state, setting us on a new trajectory. The thoughts, the feelings, the desires that flicker through our minds are the ripples on the surface of this deep, potential sea, the what-ifs, the daydreams, the imagined scenarios. These are not just idle fantasies, they are the exploration of our own personal wave function, the tracing of the different possible paths that our lives could take. And sleep is the time when we dive most deeply into this ocean of possibility. In the waking state, our consciousness is largely a collapsed wave function. We have made our choices. We are on our path. Our reality is, for the most part, definite and singular. But as we fall asleep, the collapse is undone. We decohere from the classical world and re-enter the quantum realm of pure potential. In our dreams, we are no longer bound by a single reality. We can experience a multitude of possibilities simultaneously. A dream is not a linear narrative. It is a holistic, superpositional experience, a cross-section of our own personal wave function. It can contain echoes of the past, premonitions of the future, and symbols of our deepest, timeless nature, all woven together in a single, multi-layered tapestry of meaning. To interpret a dream is to act as an observer, to collapse its rich, superpositional meaning into a single, conscious understanding. But the dream itself, in its raw, uninterpreted state, remains a pure expression of possibility. It is a reminder that our reality is not as fixed and solid as it appears. It is a reminder that we are always, at every moment, standing at the edge of an infinite sea of potential. The wave function is the universe's most beautiful and profound poem. It is a poem written in the language of mathematics, a poem that speaks of a reality that is not made of things, but of possibilities, not of certainties, but of dreams. And every night, as we close our eyes and surrender to the gentle wave-like currents of our own consciousness, we are given the chance to read a few more lines of this endless cosmic verse and to remember the deep, beautiful, and liberating truth of our own infinite potential. The universe, as described by modern physics, is a story of two grand and seemingly incompatible narratives. On the one hand, we have Einstein's theory of general relativity, the story of the large-scale cosmos, a world of smooth, curved space-time, of galaxies and black holes, a world governed by the elegant deterministic laws of gravity. On the other hand, we have quantum mechanics, the story of the small-scale world, a world of discrete particles, of probabilistic jumps, of uncertainty and superposition. These two theories are the twin pillars of modern physics, and each has been confirmed with unprecedented accuracy in its own domain, but they do not seem to speak the same language. They are based on fundamentally different principles and mathematical formalisms. Finding a single, unified theory that can encompass both a theory of quantum gravity is the single greatest challenge in all of theoretical physics. It is the Holy Grail, the quest to find the single, underlying law that governs the entire cosmos, from the subatomic to the cosmological. This tension between the large and the small, the continuous and the discrete, the deterministic and the probabilistic, is not just a problem for physicists, it is a tension that we all live with, a fundamental duality of our own experience. We live in the macroscopic, classical world of our bodies, a world governed by the seemingly predictable laws of gravity and motion. But our minds, our consciousness, often seem to operate on a different logic, a logic that is more akin to the quantum world, a world of fluid associations, of nonlinear time, of superpositional states. Sleep is the realm where this tension between the two worlds is most acutely felt, and perhaps where a bridge between them can be found. As we fall asleep, our consciousness detaches from the classical, sensory world and enters a state that is deeply quantum-like. In our dreams, the normal laws of physics are suspended. We can fly, defying gravity. We can pass through walls, an act of macroscopic quantum tunneling. We can be in multiple places at once, a direct experience of superposition. The scale of our experience becomes fluid and dynamic. In one moment, we can feel as vast as a galaxy, our consciousness expanding to fill the cosmos. In the next, we can feel as small and insignificant as a single grain of dust. This constant shifting of scale, this effortless movement between the macro and the micro, is a hallmark of the dream state. It is as if our dreaming mind is a natural quantum gravity simulator, a place where the rigid distinctions between the large and the small dissolve, and a more unified, holistic reality is experienced. Could it be that the structure of our own consciousness is a clue to the structure of the universe? Could the way our minds bridge the gap between the concrete, physical world and the abstract, symbolic world of thought be a reflection of the way that nature bridges the gap between gravity and the quantum? This is a speculative but deeply compelling idea. It suggests that the answers to the deepest questions of physics may not just be found in particle accelerators or space telescopes, but also in the deep, introspective exploration of our own inner worlds. Sleep, in this view, is not just a biological function. It is a nightly journey to the very frontier of our understanding, a place where the two great warring narratives of the universe can meet, can dance, and can perhaps, in the symbolic, poetic language of our dreams, find a way to become one. The unresolved tension between gravity and the quantum is not just a problem for science. It is the central creative tension of our own human existence, a tension that we are invited to explore, to hold, and to integrate in the deep, mysterious, and unifying space of our own sleep. In the final analysis, the deepest mystery that the quantum world presents us with is not about particles or waves, but about ourselves. The journey into the heart of the atom has led us, unexpectedly, to the threshold of our own consciousness. The discovery that the observer is not a detached spectator, but an active participant in the creation of reality, has forced science to confront a question it has long sought to avoid: what is the nature of the observer? What is this thing we call consciousness that seems to hold such a privileged and powerful place in the cosmic drama? The classical, materialistic worldview, which has dominated science for centuries, sees consciousness as an epiphenomenon, a secondary and accidental byproduct of complex neural computation in the brain. It is a ghost in the machine, a strange and wonderful illusion, but ultimately, not a fundamental aspect of reality. But the quantum world seems to hint at a different, more radical possibility. It suggests that consciousness may not be a late-coming accident in a dead, mechanical universe, but may be a fundamental, irreducible, and perhaps even primary aspect of the cosmos itself. This is the central tenet of a philosophical position known as panpsychism. The idea that consciousness, in some rudimentary form, is a property of all matter. In this view, an electron does not just have mass and charge. It also has a tiny, primitive flicker of subjective experience. As matter becomes more complex and organized, as in a living cell or a human brain, this rudimentary consciousness can combine and complexify, giving rise to the rich, multi-layered awareness that we experience. This is a staggering idea, one that completely inverts our normal understanding of the world. It suggests that the universe is not a collection of dead matter that somehow, miraculously, gives rise to consciousness. It suggests that the universe, from its very beginning, has been imbued with a potential for awareness, and that we, as conscious beings, are not a strange anomaly, but a natural and beautiful expression of this fundamental cosmic property. In this worldview, the quantum field is not just a field of energy and potential, it is also a field of nascent consciousness. The entire universe is a single, vast, and interconnected mind, and our individual consciousnesses are like eddies in this great cosmic stream. This is a vision that has been expressed, in different forms, by mystics and philosophers for millennia. The Brahman of the Vedanta, the mind of God of the Hermetic traditions, the anima mundi of the Platonists. These are all expressions of the same deep intuition that consciousness is the ultimate reality. What is new is that this ancient, spiritual intuition is now finding a tentative, but growing, resonance with the cutting edge of modern physics, the puzzles of the quantum world. The observer effect, entanglement, the nature of time may all be clues that are pointing us towards a new, post-materialist paradigm, a paradigm that recognizes the fundamental role of consciousness in the structure of reality. And sleep, once again, becomes our most intimate and direct portal to this deeper reality. As the conscious individual ego dissolves, we are given the chance to merge back into the universal field of consciousness from which we arose. The dream state, with its symbolic language, its non-local connections, and its creative power, may be a direct experience of the mind of the universe, expressing itself through the unique filter of our own personal history. To fall asleep is to remember our cosmic origins. It is to let go of the illusion of our own separateness and to reunite with the single, unified, and conscious field that is the source of all being. We are not just in the universe is in us. We are the universe's way of knowing itself, of feeling itself, of dreaming itself into existence. And the greatest secret of the quantum world may be a secret that we have known all along, in the deepest, most silent, and most sacred chambers of our own conscious hearts. The strange, paradoxical, and beautiful world of quantum mechanics is not a distant, abstract realm of interest only to physicists. It is the very ground of our being, the invisible, energetic, and conscious foundation upon which our entire reality is built. The principles of superposition, of uncertainty, of entanglement, are not just descriptions of subatomic particles. They are deep, resonant metaphors for the nature of our own minds, our own lives, our own souls. The universe that the quantum revolution has revealed is not a dead and deterministic machine, but a living, breathing, and participatory cosmos. A universe that is constantly being co-created in the dance between potential and actuality, between the observer and the observed, and sleep, the state we enter every night, is our most profound and direct access to this quantum reality. It is a nightly pilgrimage to the source, a journey into the superpositional sea of our own consciousness, a surrender to the creative uncertainty of the void, an immersion in the entangled web of our own interconnectedness. To understand the quantum world is to understand ourselves in a new and deeper way. It is to recognize that we are not fixed, solid, and separate entities, but fluid, multi-layered, and deeply connected beings. It is to embrace the paradox of our own nature, to honor both the particle of our individual existence and the wave of our universal connection. It is to find a new kind of freedom, a freedom that comes not from control, but from surrender, a freedom that is born from the recognition that at the heart of reality lies not a rigid certainty, but an infinite, creative, and beautiful mystery. The journey into the quantum realm is a journey home, a journey back to the fundamental, magical, and dreamlike nature of our own true being. And every night, as we close our eyes and drift into the gentle quantum sea of sleep, we are given the chance to remember, to heal, and to be reborn.
What if the fabric of reality itself was written in a language we are only beginning to understand? What if beneath the seemingly solid world we see, there exists a realm where particles can be in two places at once, where information defies intuition, and where probability is not just a concept, but the very foundation of existence? At the heart of this mystery lies an equation, one that has reshaped our understanding of the universe at its most fundamental level. This is Schrödinger's equation, the mathematical backbone of quantum mechanics. It is not merely a formula, it is a map, a guide to the strange and beautiful world of quantum physics. It tells us how particles move, how they interact, and most intriguingly, how reality itself is shaped by probabilities. Without this equation, our comprehension of the universe at its smallest scales would unravel. But what if we could do more than just understand? What if we could harness these quantum principles, not just to study reality, but to build something entirely new? Unlike classical computers, which process information in a rigid, binary fashion, quantum computers embrace uncertainty, complexity, and superposition, mirroring the quantum world itself. They are not just machines, they are a glimpse into the deeper workings of reality, a key to problems once thought impossible to solve. In 1980, physicist Paul Benioff envisioned a machine that didn't rely on traditional bits, but on quantum bits, qubits, tiny units of information that obeyed the strange laws of quantum mechanics. This was the first step toward what we now call quantum computing. At the time, it seemed like science fiction. Classical computers were getting faster, but when physicists tried to use them to simulate quantum systems, they hit a wall. The problem wasn't just speed, it was complexity. The quantum world is exponentially more intricate than what classical computers can handle. This challenge captivated brilliant minds like Yuri Manin and Richard Feynman, who proposed something revolutionary. To truly understand quantum mechanics, we needed computers that worked like quantum systems themselves. Their insights would lay the foundation for a technological revolution, one that would not only redefine computing, but also reshape fields like cryptography, communication, and artificial intelligence. What if the rules we thought governed reality were just an approximation of something deeper? What if the universe, at its most fundamental level, operated on principles so alien to our everyday experience that even our most powerful classical computers struggled to comprehend them? In a world where information has long been defined by simple binary states, zeros and ones, a new frontier is emerging, one that does not just compute, but redefines the very essence of computation itself. This is the world of quantum computing, where probabilities replace certainties, entanglement defies locality, and computational power reaches unfathomable scales. To understand this revolution, we must first explore the fundamental differences between classical and quantum computation. Classical computers have been the backbone of technological progress for decades, driving everything from meteorological modeling to digital photography. At their core, these machines process information using bits, discrete units that can be either a 0 or a 1. Every computational task, no matter how complex, is ultimately reduced to a vast sequence of binary switches flipping between these two states. Consider a meteorological prediction system. The temperature, pressure, humidity, and wind patterns are all converted into binary data, which is then processed through intricate models to forecast the weather. Similarly, in digital photography, each pixel in an image is represented as a series of bits that encode color and intensity. These processes work efficiently because they follow a structured, linear pathway of computation. But what happens when problems become too complex for this step-by-step approach? Some problems grow exponentially in complexity, making them nearly impossible for classical machines to solve within a reasonable time frame. Take molecular simulation, for example. Understanding the behavior of a single molecule requires accounting for the quantum interactions of its constituent atoms, a task that classical computers struggle with because they must process each interaction sequentially. Similarly, optimization problems, such as finding the most efficient routes for delivery trucks or determining the optimal way to schedule airline flights, quickly become intractable as the number of variables increases. Classical computers must evaluate each possibility one at a time, making these tasks inefficient as the complexity scales. Quantum computers, however, operate under entirely different principles. Instead of bits, they use qubits, which exploit the bizarre properties of quantum mechanics to encode information in multiple states simultaneously. This is known as superposition. A single qubit can exist in a combination of both 0 and 1 at the same time, rather than being restricted to just one or the other. This allows quantum computers to perform multiple calculations in parallel. To visualize this, imagine trying to guess a 4-digit PIN. A quantum computer, on the other hand, could evaluate all possible combinations simultaneously, drastically reducing the time needed to arrive at the answer. This is what gives quantum computing its enormous computational advantage. Beyond superposition, quantum computers leverage another phenomenon, entanglement. When two qubits become entangled, their states become linked such that the state of one qubit instantly determines the state of the other, regardless of the physical distance between them. This property allows quantum systems to share and process information in ways that classical computers simply cannot. Entanglement enables quantum computers to solve complex problems with an efficiency that seems almost magical. Instead of processing data in isolation, entangled qubits communicate instantaneously, allowing quantum systems to work as a unified whole. This interconnectedness dramatically enhances computational power and opens new possibilities for fields such as cryptography and material science. A single qubit may not seem impressive on its own, but as more qubits are added, their computational potential grows exponentially. With just 300 qubits, a quantum computer can represent more states simultaneously than there are particles in the observable universe. This level of computational capacity is incomprehensible to classical computing systems, which would require an astronomical amount of memory to achieve the same feat. Today, most secure communication systems rely on encryption methods like RSA, which is based on the difficulty of factoring large numbers. The security of RSA depends on the fact that multiplying two large prime numbers is easy, but reversing the process, factoring the product back into its prime components, is incredibly hard for classical computers. For example, a 2048-bit RSA encryption key is so computationally demanding to break that it would take a classical supercomputer millions of years to solve. However, with quantum computing and Shor's algorithm, this problem becomes trivial. Shor's algorithm allows quantum computers to factor large numbers exponentially faster than classical methods, rendering RSA encryption effectively obsolete. This has led to a race to develop post-quantum cryptography, encryption techniques that remain secure even in the presence of quantum attacks. Beyond cryptography, quantum computers excel in optimization problems, finding the most efficient solutions from an overwhelming number of possibilities. Consider logistics. Companies like FedEx and Amazon rely on complex routing algorithms to optimize delivery paths. While classical computers can approximate solutions, they cannot process all possibilities at once. Quantum computers, however, can explore all potential routes simultaneously, identifying the most efficient path almost instantly. This capability could revolutionize industries ranging from transportation to finance, enabling unparalleled efficiency gains. Despite their immense potential, quantum computers are not a replacement for classical machines. They are not universally better. Rather, they excel at specific types of problems that involve massive complexity and parallel computation. Everyday tasks, such as checking emails, browsing the web, or running spreadsheets, remain firmly within the domain of classical computing. Running a quantum computer for these mundane tasks would be akin to using a spaceship for a daily commute, overkill and highly impractical. Moreover, the current state of quantum hardware presents significant challenges. Qubits are fragile, highly susceptible to interference from their environment, and require extreme conditions, such as temperatures near absolute zero, to function properly. Error correction remains one of the biggest obstacles to scaling quantum computers for practical applications. Without breakthroughs in stability and fault tolerance, quantum computers will remain confined to highly specialized uses. Most quantum computers today are still in the experimental phase. Companies like Google, IBM, and Rigetti Computing are developing quantum processors, but these systems currently have limited practical applications. Google's Sycamore processor, for instance, was able to perform a calculation in minutes that would take the fastest supercomputers thousands of years. However, such demonstrations remain highly specialized and not yet applicable to everyday computing needs. At the same time, artificial intelligence has been making its own leaps forward, raising the question of whether AI and classical computing might solve some of the same problems once thought to require quantum computing. AI excels at pattern recognition and learning from vast datasets, while quantum computing is uniquely suited for problems involving complex system interactions. Rather than competing, these technologies will likely complement each other, each bringing its own strengths to the table. Some physicists, like Seth Lloyd, have even speculated that the universe itself may function like a quantum computer. If every interaction between particles represents a fundamental computation, then quantum mechanics might be the key to understanding the very fabric of reality. Recent experiments using quantum processors, such as simulations of wormhole-like behavior, hint at the potential of quantum computing to model some of the most profound mysteries of physics. This experiment underscores a deeper idea that quantum computing is not merely a technological breakthrough, but a conceptual revolution. The principles that underpin quantum computation, superposition, entanglement, and quantum interference, mirror the very laws that govern the universe at its most fundamental level. Theoretical physicist Seth Lloyd once proposed that the universe itself may be a vast quantum computer, where every particle interaction represents a fundamental computation. From the spin of an electron to the evolution of galaxies, reality might unfold as a vast ongoing quantum calculation. While this notion remains speculative, it serves as a compelling framework for understanding both quantum computing and the universe itself. Unlike classical computation, which follows a linear, step-by-step progression, quantum mechanics suggests that reality explores multiple potential outcomes simultaneously before collapsing into a single observed state. This eerie parallel between computation and existence fuels some of the most profound philosophical questions in modern physics. As we advance in our pursuit of quantum computation, we must temper our expectations with a clear understanding of its limitations. Quantum computers are not destined to revolutionize everyday computing. They will not replace our laptops, stream our favorite shows, or run consumer applications. Their role is far more ambitious: to tackle the unsolvable, to simulate the unimaginable, and to probe the very foundations of reality. If successful, they could redefine our understanding of materials, medicine, artificial intelligence, and even the nature of the cosmos. In the grand scheme of technological progress, quantum computing is not a convenience. It is an expedition. It will not make life simpler, but it may reveal truths that have eluded us for centuries. It will not replace classical computers, but it will expand the boundaries of computation in ways we are only beginning to fathom. And in doing so, it might just unlock the deepest secrets of the universe itself. If that is not extraordinary, what is?
Time moves forward, relentless and unyielding, carrying the universe from its fiery birth to a distant, quiet end. Stars burn, galaxies spin, and planets turn. But this cosmic dance is not eternal. Everything decays, from the smallest atom to the grandest galaxy, far beyond our lifetimes. In a future spanning trillions of years, the universe will transform, its familiar rhythms fading into a cold, silent stillness, a reality where the laws of physics play out to their strangest conclusions. The universe we know is alive with light. At night, the sky glimmers with stars, each a furnace fusing hydrogen into helium, casting warmth across vast distances. These stars, scattered through billions of galaxies, are the heartbeat of the cosmos, their glow a blend of a universe in its prime. But this brilliance is temporary, a fleeting moment in a story that stretches far beyond human comprehension. Stars are not eternal, they are engines with finite fuel, destined to burn out, leaving behind a darker, quieter universe. Stars are born in clouds of gas, collapsing under gravity to ignite in nuclear fusion. A star like our Sun burns steadily for billions of years, its core a cauldron where hydrogen fuses into helium, releasing energy that lights the heavens. But fuel runs low. When hydrogen dwindles, the core contracts, heating to fuse helium into carbon and oxygen. The star swells into a red giant, its outer layers glowing crimson, before shedding them to form a planetary nebula, leaving a white dwarf, a dense, cooling core no larger than Earth. This fate, mapped in the 1930s by Subrahmanyan Chandrasekhar, applies to stars below a critical mass, now called the Chandrasekhar limit. Heavier stars meet a more dramatic end. When their cores exhaust fuel, they collapse under gravity, triggering a supernova explosion that outshines entire galaxies. The core may become a neutron star, a city-sized sphere of unimaginable density, or a black hole, a void where gravity traps even light. Chandrasekhar's calculations showed that stars above the limit follow this path, their remnants enduring long after the explosion fades. These processes fusion, collapse. Explosion are the universe's machinery, but they rely on finite resources, and the cosmos is running out of raw materials. The universe was once a nursery of stars, with vast gas clouds birthing new suns in a frenzy of creation. But those clouds are depleting. Each star formed consumes gas, and supernovas scatter some into space, but much is locked away in white dwarfs, neutron stars, and black holes. Over billions of years, the star formation rate slows, a trend already observable today. In 10 trillion years, the galaxies will birth fewer stars, their fuel reserves nearly spent. By 100 trillion years, the process will nearly halt, leaving a universe where new light is a rarity. This decline is not sudden, but gradual, a fading glow across cosmic time. Stars like our Sun, with lifespans of 10 billion years, will be long gone. Even red dwarfs, the smallest and slowest burning stars, which can shine for trillions of years, will eventually exhaust their hydrogen, their fusion will falter, and they'll cool into white dwarfs, joining the silent remnants of their brighter kin. The last red dwarf, perhaps the final spark of warmth, will flicker out in a future so distant it defies imagination, marking the end of the stellar era. What remains is a universe of leftovers, White dwarfs, now cold and dark, drift through the void, their surfaces no longer glowing. Neutron stars, dense and silent, spin slowly, their magnetic fields faded. Black holes, the densest relics, lurk in the darkness, swallowing stray matter. Rogue planets, ejected from their systems, wander frozen, their surfaces locked in eternal ice. These objects, scattered across a universe stretched thin by expansion, are the cosmic fossils of a once vibrant epoch, a testament to the impermanence of light and heat. This phase, known as the degenerate era, is a stark departure from the universe we know. There are no galaxies aglow with starlight, no nebulae birthing new suns. Space is vast, its distances growing as the universe expands, driven by dark energy that pushes everything apart. The galaxies, once tight spirals and clusters, have merged or drifted, their stars extinguished. What's left is a cold, quiet expanse, where objects are so far apart they rarely interact, a universe where motion slows and energy fades. The degenerate era underscores the universe's entropy, the tendency for order to dissolve into disorder. Stars once drove energy from hot cores to cooler surfaces, powering fusion and light. But in this era, there's no heat to flow, no gradient to fuel work. White dwarfs and neutron stars, though dense, are inert, their energy spent. The universe is not dead in a dramatic sense, but still, like a clock wound down so far, it cannot tick. Matter exists: black dwarfs, neutron stars, rogue planets, but it's meaningless, isolated, unable to form new systems or spark new life. This stillness is a natural outcome of physics, not a break from it. Thermodynamics dictates that energy disperses, that systems decay. The universe, following these rules, has run its course, its vibrant youth replaced by a quiet middle age. Yet this is not the end. The degenerate era, stretching across unimaginable timescales, is a prelude to stranger transformations. Black holes, the brilliant giants of this epoch, will play a role. Their slow decay a sign that even the densest objects are not eternal. The human perspective on this future is humbling. We live in a fleeting moment, a time when stars still shine, when galaxies still dance. Our lives, measured in decades, are a blink against the trillions of years that lie ahead. Yet we imagine this future, tracing the path of physics to its limits, asking what becomes of the cosmos when all we know is gone. This is a deeply human act, a search for meaning in a universe that will outlast us, a reflection on our place in a story that began with light and will end in silence. The melancholic beauty of this narrative lies in its inevitability. The stars, so bright today, are destined to fade, their light a temporary gift. The galaxies, vast and swirling, will dissolve into the dark, their stories lost to time. Yet there is wonder in this decay, in the way the universe follows its laws with unwavering precision, transforming from a blaze of creation to a quiet drift of remnants. The degenerate era, with its cold relics, is a testament to this transformation, a stage where the cosmos rests before its next act. This journey through the universe's decline is a reminder of our fleeting existence. The stars that guide our nights, the galaxies that fill our telescopes, are part of a brief chapter, a moment when the universe is alive with possibility. As we look to the future, we see not just the end of light, but the persistence of physics, the rules that carry the cosmos forward even as it grows cold. The story of the universe's end is not yet complete. Its next phase waiting in the shadows, ready to unfold in ways that challenge our understanding of reality itself. The universe, once aglow with stars, has faded into a cold, dark expanse, its galaxies dimmed and its starlight extinguished. In this vast silence, black holes emerge as the silent rulers, their immense gravity shaping a cosmos stripped of warmth and motion. Over timescales stretching beyond imagination, these enigmatic relics decay through a subtle process, revealing a universe where even the mightiest structures surrender to the relentless march of time. The degenerate era, where white dwarfs and neutron stars drifted in isolation, has given way to a new chapter, the black hole era. Stars are gone, their fusion silenced, leaving behind a universe of remnants. Galaxies, once vibrant spirals, are now dark, their light lost to the cooling of red dwarfs and the collapse of massive suns. In this emptiness, black holes stand as the last bastions of structure, formed from the deaths of stars, galactic collisions, or the merging of smaller voids. They are not mere objects but gravitational giants, warping space-time so fiercely that nothing, not even light, can escape their grasp. Black holes are the universe's long-term survivors, enduring where stars and planets have faded. A stellar mass black hole, born from a supernova, may have the mass of 10 suns compressed into a point smaller than an atom. Supermassive black holes, lurking at galactic centers, hold the mass of billions of suns, their influence stretching across light years. In the black hole era, these objects dominate, scattered across a universe expanded so vastly by dark energy that galaxies are mere memories, their remnants spread too far to interact. Gravity drives this epoc's slow ballet. Black holes drift, their paths shaped by the faint pull of distant masses. Some collide, merging to form larger voids, their event horizons rippling as they coalesce. Others accrete stray matter-rogue planets, cold dwarfs, or cosmic dust drawn too close by gravity's unyielding embrace. These interactions are rare, as space has stretched to isolate most objects. But when they occur, they are moments of cosmic drama, brief sparks in an otherwise silent void. Over trillions of years, even these collisions dwindle, leaving black holes as solitary sentinels in a universe grown impossibly vast. This era is not eternal, for black holes, despite their might, are not immune to decay. In the 1970s, Stephen Hawking revealed a startling truth. Black holes evaporate through a process now called Hawking radiation. The vacuum of space, far from empty, is alive with quantum fluctuations, where virtual particle pairs matter and antimatter briefly appear and annihilate. Near a black hole's event horizon, the boundary beyond which nothing escapes. These pairs can be split. One particle falls into the void, while the other escapes, carrying a sliver of the black hole's energy. This escaping particle, a photon or other lightweight entity, slowly drains the black hole's mass. Hawking radiation is vanishingly slow. For a stellar mass black hole, the process takes 10 to the 67th years, a number so vast it dwarfs the universe's current age of 13 billion years. Supermassive black holes, with their greater mass, require even longer, up to 10 to the 100th years. A timescale that makes the degenerate era seem fleeting. Each radiated particle is a minuscule loss, but over these immense spans, the losses accumulate, shrinking the black hole until it vanishes in a final burst of radiation, a quiet puff rather than a cataclysmic explosion. This evaporation is a triumph of quantum mechanics, showing that even black holes, the universe's most unyielding structures, are subject to the laws of physics. The process is imperceptible on human timescales, but in the black hole era, time is no constraint. The universe, patient and indifferent, waits as black holes fade, their mass converted into a thin spread of photons and other particles. As the last black hole evaporates, the cosmos loses its final anchors of gravity, leaving a near-perfect vacuum, a stage where the actors have departed and only the faintest traces remain. The black hole era is a study in contrasts. Black holes are both eternal and ephemeral, dominating the universe for eons, yet doomed to dissolve. They are invisible, their presence known only by their gravitational pull, yet they shape the cosmos' structure, gathering matter and merging in silent dances. Their decay, through Hawking radiation, is a microcosmic process, quantum fluctuations at the event horizon, yet it plays out on the grandest scales, transforming the universe over unimaginable timescales. This interplay of the small and the vast is a hallmark of the cosmos' evolution, a reminder that even the mightiest entities are bound by the same rules that govern the smallest particles. The human perspective on this era is one of awe and humility. We live in a time of light where stars illuminate the night and galaxies tell stories of creation. The black hole era, by contrast, is a future where light is a memory, where the universe is a graveyard of gravitational ghosts. Our existence, a mere flicker in cosmic time, seems insignificant against the backdrop of 10 to the 100th years. Yet we imagine this future, piecing together its story through equations and observations. This act of imagination, of reaching across eons to understand the cosmos' fate, is a deeply human endeavor, a search for meaning in a universe that will outlast us all. The melancholic beauty of the black hole era lies in its quiet persistence. The universe, stripped of its stars, continues its slow transformation, driven by gravity and quantum mechanics. Black holes, once symbols of destruction, become relics of endurance, their evaporation a gentle farewell rather than a violent end. This era, spanning timescales beyond comprehension, is a testament to the universe's patience, its ability to follow its laws through the darkest, most silent phases of its existence. The black hole era also raises profound questions about information and loss. As black holes evaporate, what happens to the information they held? The details of the matter they consumed. Hawking initially argued this information was lost, but later theories suggest it may be preserved in the radiation, encoded in ways we cannot yet fully grasp. This debate, central to modern physics, hints at deeper truths about the universe's structure, truths that may persist even as black holes fade. The question of information's fate is a thread that will weave into the cosmos's later stages as the universe grows emptier still. The end of the black hole era marks a turning point. With the last black hole gone, the universe is a near-empty void, its only contents a scattering of subatomic particles and radiation, stretched thin by relentless expansion. This is not the final act, but a transition, a stage where the absence of structure allows new physics to emerge. The particles that remain, the relics of stars and black holes, face their own decay, setting the scene for a cosmos where even the building blocks of matter may not endure. This journey through the universe's decline is a reflection on permanence and change. The black holes, so dominant in this era, are not eternal. Their decay, a reminder that nothing escapes the laws of physics. The cosmos, once a place of creation, is now a realm of dissolution, yet its story continues, driven by the quiet persistence of quantum processes and the inexorable stretch of space. As we look to the future, we see a universe poised for stranger transformations, where the rules of reality may shift in ways that challenge our deepest understanding. The universe, stripped of stars and black holes, lingers as a vast, cold void, its only remnants a scattering of particles adrift in endless space. In this desolate expanse, even protons, the sturdy cores of atoms, may decay, unraveling the last traces of matter into a faint sea of radiation. This quiet dissolution, unfolding over unimaginable timescales, transforms the cosmos into a realm where solidity vanishes, leaving only whispers of what once was, a testament to the impermanence of all things. The black hole era has ended, its final voids evaporating into photons through Hawking radiation, leaving a universe nearly empty. White dwarfs, neutron stars, and rogue planets persist. Cold relics of a bygone age, but they are sparse, isolated by the relentless expansion driven by dark energy. These remnants, once part of vibrant galaxies, now drift in a cosmos stretched so thin that interactions are rare. The universe is a silent archive, its history etched in these frozen fossils, but even they are not eternal. A new process, proton decay, threatens to erase the last vestiges of matter, ushering in a post-decay radiation era. Protons are the backbone of atoms, residing in their nuclei alongside neutrons, surrounded by electrons. Their stability has long been assumed, a foundation for matter's endurance. Every rock, every planet, every neutron star depends on protons' permanence. Yet grand unified theories, developed by physicists like Howard Georgi and Sheldon Glashow in the 20th century, suggest protons may not last forever. These theories, which aim to unify the strong, weak, and electromagnetic forces, predict that protons decay into lighter particles, positrons, photons, or neutrinos over timescales so vast they dwarf the black hole era. The predicted lifetime of a proton is staggering at least 10 to the 34th power years, a number that makes the universe's current age of 13 billion years seem instantaneous. This is not a process we can observe. No experiment has yet detected proton decay, and the odds are so low that a single proton's decay is a cosmic rarity. But in a universe with infinite time, rarity becomes certainty. Given enough protons and enough years, trillions of trillions, the decay accumulates, each proton crumbling silently, its energy released as fleeting radiation. In the post-black hole era, the universe's remnants are prime candidates for this decay. Black dwarfs, the cooled husks of white dwarfs, are dense with carbon and oxygen nuclei, each packed with protons. Neutron stars, though dominated by neutrons, contain proton-rich layers. Rogue planets, frozen worlds of rock and ice, are built from atoms with proton cores. Over 10 to the 35th years, these objects begin to disintegrate, not through violence, but through a slow, statistical unraveling. Protons decay, their nuclei breaking apart, leaving positrons and photons that scatter into the void. This decay is not a fiery end, but a quiet erosion. A black dwarf, once a solid sphere, loses its structure as protons vanish, its matter dissolving into a diffuse cloud of radiation. A neutron star's proton-rich surface crumbles, its stability fraying. By 10 to the 40th power years, most protons are gone, their decay complete. What remains is a universe without atoms, without solids, without the building blocks that once formed stars and planets. The cosmos is now a thin, ghostly expanse, filled with photons, neutrinos, and other lightweight particles, stretched ever thinner by expansion. This post-decay radiation era is a stark departure from the universe's earlier vibrancy. There are no galaxies, no stars, no black holes, only a near-empty vacuum where particles drift, too distant to interact. The universe's energy, once concentrated in fusion and gravity, is now diffuse, a faint hum of radiation that carries no warmth, no potential for creation. This is entropy at its extreme, where the cosmos has no gradients left to fuel change. The particles exist, but they are meaningless, a silent testament to a reality where matter has lost its purpose. The physics of proton decay is a triumph of theoretical insight, rooted in the Standard Model and its extensions. Grand unified theories, proposed in the 1970s, suggest that at high energies of the early universe, the fundamental forces were one. As the cosmos cooled, these forces split, but protons retained a faint instability, a memory of that unity. The decay process, though speculative, follows from these principles, a prediction that no new forces are needed, just the slow, inevitable work of quantum mechanics over eons. If protons are stable, as some models allow, the universe might linger longer in its degenerate state, but the possibility of decay paints a bleaker, more transient picture. The human perspective on proton decay is one of profound disconnection. We live in a world of matter, where atoms form the ground beneath us, the air we breathe, the stars we see. The idea that these atoms could dissolve, not in a cataclysm, but in a slow, silent fade, challenges our sense of permanence. Our lives, measured in heartbeats, are infinitesimal against 10 to the years, a timescale that renders human existence a fleeting whisper. Yet we ponder this future, using mathematics to trace the cosmos's path, a testament to our need to understand even what lies beyond our grasp. The melancholic beauty of this era lies in its quiet dissolution. The universe, once a place of creation, is now a realm of decay, where even the sturdiest particles surrender to time. The post-decay radiation era, with its sparse, drifting particles, is a cosmos stripped bare, its vibrancy replaced by a stillness that feels eternal yet fragile. This is not an end, but a transition, a stage where the absence of matter sets the scene for stranger possibilities, where the universe's very fabric may shift in ways we cannot predict. The human connection to this narrative is both humbling and profound. We are made of protons, our bodies a temporary assembly of atoms destined to outlast us, yet not forever. The idea that these atoms could decay, leaving only radiation, mirrors our own impermanence, a reminder that all things, from stars to selves, are bound by the same laws. Yet, in imagining this future, we assert our place in the cosmos, our minds reaching across eons to grapple with a reality that will unfold long after we are gone. The post-decay radiation era also raises questions about information and existence. As protons decay, do they leave a trace of their history, or is their information lost? The debate over black hole information, sparked by Stephen Hawking, finds an echo here. As the universe's final particles fade into the void, these questions, rooted in quantum mechanics, hint at deeper truths about the cosmos's structure, truths that may persist even as matter dissolves. The radiation that remains, stretched thin by expansion, is a faint archive, carrying the universe's story into its next, stranger phase. This journey through the universe's decline is a reflection on change and loss. The protons that built our world, so stable in our time, may crumble, their decay a quiet end to matter's reign. The cosmos, now a sea of radiation, is poised for further transformations, where the rules of physics may bend in ways that defy our understanding. The story of the universe's end continues, its next act waiting in the silent expanse, ready to unfold in a reality where even emptiness holds secrets. The universe, reduced to a faint sea of radiation, stretches endlessly, its matter dissolved and its forces silenced. In this near-empty void, a subtle instability looms: vacuum decay, a quantum shift that could rewrite the laws of physics themselves. This silent transformation, lurking in the cosmos's deepest future, threatens to erase the last vestiges of our reality. A final act where even the fabric of existence may unravel, leaving a universe unrecognizable. The post-decay radiation era, where protons have crumbled into photons and neutrinos, marks a cosmos stripped of structure. No stars, no black holes, no atoms, remain only a sparse, cold expanse, its particles too distant to interact, spread thin by relentless expansion. This is a universe at maximum entropy, where energy gradients have vanished, and change seems impossible. Yet, even in this stillness, the vacuum, the underlying field that defines space, is not inert. It holds a hidden fragility, a potential to shift into a state that could alter reality's foundations, a process known as vacuum decay. The vacuum is not empty but a dynamic stage, shaped by fields like the Higgs field, which gives particles their mass. The Higgs field, discovered in 2012, sets the rules for our universe, allowing atoms to form, stars to burn, and life to exist. Its value, finely tuned, creates a stable reality, but stability may be an illusion. Theoretical physicists, including Gianfrancesco Giudice and John Ellis, calculated that our vacuum might be metastable, not at its lowest energy state. A deeper, more stable vacuum could exist, and if our universe's vacuum were to shift to this state, the consequences would be profound. Vacuum decay begins with a quantum fluctuation, a random blip in the fabric of space where the Higgs field's value changes. This fluctuation creates a bubble of true vacuum, a region governed by new physical laws. Unlike our vacuum, where particles have specific masses and forces interact predictably, this new state could render atoms impossible, disrupt gravity, or erase time itself. The bubble, once formed, expands at nearly the speed of light, converting the surrounding metastable vacuum into its own reality. There's no explosion, no heat, just a silent replacement, a rewriting of existence itself. This process is not a distant fantasy, but a consequence of quantum mechanics, where probabilities govern even the universe's fate. The likelihood of vacuum decay is vanishingly small, so low that it might not occur for 10 to the 100th power years, a timescale that dwarfs proton decay's 10 to the 34th power years. Yet, in an infinite universe, even the smallest odds become certainties. The vast emptiness of the post-decay era, with its endless space and time, offers countless opportunities for a fluctuation to spark a bubble, transforming the cosmos in an instant. The implications of vacuum decay are staggering. Inside the bubble, the laws of physics could be incompatible with matter, energy, or structure as we know them. Electrons might lose their charge, gravity might weaken, or space itself might collapse. The universe we know, its constants, its forces, its very essence would vanish, replaced by a reality we cannot predict. It might be a flat nothingness, a void without form, or a new cosmos with alien rules, where stars and life are impossible. This is not destruction but irrelevance, a shift where our physics becomes a forgotten footnote. The human perspective on vacuum decay is both unsettling and awe-inspiring. We live in a universe where the Higgs field's delicate balance allows our existence, a fleeting moment of stability in a cosmic timeline that stretches beyond comprehension. The idea that this balance could shift, not through cataclysm but through a quiet quantum event, challenges our sense of permanence. Our lives, our world, our entire reality could be erased, not by force, but by probability, a reminder of our fragility in a cosmos governed by chance. The science of vacuum decay is rooted in the Standard Model and its extensions. The Higgs boson's mass, measured at the Large Hadron Collider, suggests our vacuum is near the edge of metastability, a precarious state where a lower energy vacuum is possible. Calculations by Giudice and Ellis show that our universe's constants, the Higgs boson's mass, The top quark's properties place it uncomfortably close to instability. While we may be safe for eons, the possibility of decay is real, a prediction that requires no new physics, only the quantum rules that govern our reality today. The melancholic beauty of vacuum decay lies in its silent inevitability. The universe, already stripped of stars and matter, faces a final transformation, not through violence, but through a subtle shift in its essence. The post-decay radiation era, with its sparse particles, is a cosmos on the brink. Its vacuum, a fragile canvas waiting for a quantum brushstroke. This is a story of endings, where even the rules that define existence may fade, leaving a reality where nothing familiar remains. The human connection to this narrative is profound. We are products of a stable vacuum, our atoms and thoughts shaped by the Higgs field's delicate balance. The idea that this balance could collapse, erasing the physics that sustains us, mirrors our own mortality, a reminder that all things, from particles to people, are temporary. Yet in pondering vacuum decay, we assert our place in the cosmos, our minds reaching across unimaginable timescales to grapple with a future that defies comprehension. This act of imagination, of seeking meaning in the face of nothingness, is a deeply human endeavor. The implications of vacuum decay extend beyond our universe. If a bubble forms, it might not be the first. The cosmos could be part of a multiverse, where other bubbles have sparked new realities with different laws. This idea, explored by physicists like Andrei Linde and Alexander Vilenkin, suggests our universe is one of many, each born from a quantum fluctuation in an inflating landscape. Vacuum decay, then, is not just an end, but a potential beginning, a branching point where new universes might emerge, each with its own story. The question of information persists in this era. As the vacuum shifts, what happens to the universe's history, the details of stars, planets, and lives? The debate over black hole information, where data may be preserved or lost, finds an echo here. If our vacuum decays, the information encoded in our reality, every particle's spin, every photon's path might be erased or transformed, a loss that raises profound questions about the nature of existence. These questions, rooted in quantum mechanics, will carry into the cosmos's final phase, where even emptiness holds possibilities. This journey through the universe's decline is a reflection on fragility and change. Vacuum decay, a quiet shift in the cosmos's foundation, threatens to erase the rules that define our reality, leaving a universe where the familiar is irrelevant. The cosmos, now a near-empty void, is poised for its strangest act, where quantum mechanics and probability take center stage, shaping a future where even nothingness may give rise to something new. The story of the universe's end continues, its final chapter waiting in the silent expanse, ready to unfold in ways that challenge our deepest understanding. The universe, a near-empty void of fading radiation, drifts in silent expanse, its reality teetering on the edge of quantum uncertainty. In this final epoch, random fluctuations spark fleeting structures, particles, minds, even new universes, while time itself loses meaning, dissolving into a timeless stillness. This journey, from starlight to nothingness, reflects humanity's quest to understand a cosmos that outlives us, a narrative of endings and possibilities, where the silent folds of space whisper eternal questions. The vacuum decay era, where the universe's physical laws could shift, has left a cosmos stripped bare, its protons decayed, its black holes evaporated, its stars and galaxies long gone. Only a faint scattering of photons and neutrinos remains. spread so thin by relentless expansion that interactions are impossible. This is a universe at its most desolate, a realm where entropy reigns supreme and change seems a distant memory. Yet, even in this emptiness, quantum mechanics persists, its probabilistic nature sparking rare, strange events that challenge our understanding of existence, time, and reality itself. Quantum fluctuations, the universe's last actors, are the heart of this epoch. In the vacuum, space is not truly empty, but a seething field of virtual particles, popping into and out of existence in fleeting pairs. Normally, these pairs annihilate instantly, leaving no trace. But in a universe this vast and quiet, their effects linger. Over timescales beyond comprehension, 10 to the 100th power years or more, these fluctuations can produce not just particles, but complex structures. A single atom, a molecule, or even a fully formed brain could emerge. A phenomenon known as a Boltzmann brain, named for Ludwig Boltzmann's 19th century work on statistical mechanics. Boltzmann brains are not science fiction, but a statistical inevitability in an infinite universe. Given enough time, quantum randomness can assemble anything, no matter how improbable. A brain, complete with memories of a life it never lived, might flicker into existence. Think for a moment, then dissolve back into the void. These are not living beings, but fleeting mirages, their thoughts as transient as the fluctuations that birthed them. The paradox is unsettling in this future. Such random minds might outnumber those that evolved naturally, raising questions about consciousness and reality. If most minds are Boltzmann brains, are our own thoughts mere statistical blips? This epoch is not just about brains, but about possibility. Quantum fluctuations could spawn not just particles, but entire regions of space with new physical laws. A fluctuation might trigger a quantum tunneling event, shifting a patch of vacuum to a different state, potentially birthing a new universe. This idea, explored by physicists like Andrei Linde and Alexander Vilenkin, suggests our cosmos is one bubble in an eternally inflating multiverse, where new universes form as others fade. These bubbles, stable or fleeting, could carry alien physics, their constants and forces unlike our own, each a fresh start in a cosmic forest of possibilities. The concept of time itself falters in this era. Time, as Sean Carroll and others have argued, is tied to entropy, the arrow from order to disorder, in a universe at maximum entropy, where no gradients drive change. Time's direction blurs. Without events to mark one moment from another, no stars forming, no particles colliding, time becomes a frozen frame, a paused video with no motion to distinguish past from future. Quantum fluctuations, like Boltzmann brains or new universes, are too rare and isolated to create a narrative, leaving a cosmos where time exists but lacks meaning, a silent ticking without a clock. Reflecting on this narrative, we see a universe transformed from a blaze of starlight to a quiet void, its story unfolding through inevitable decay. The stars faded, their fuel spent, leaving white dwarfs and neutron stars in a degenerate era. Black holes ruled, then evaporated, their mass lost to Hawking radiation. Protons decayed, dissolving matter into radiation. And vacuum decay threatened to rewrite physics itself. Now, quantum fluctuations spark fleeting structures, a final act where randomness reigns. This journey, spanning trillions of years, is a testament to physics' unyielding logic, each phase a consequence of the laws that govern our reality today. The human connection to this story is profound. We are fleeting beings, our lives a blink against the cosmos's timeline, yet we imagine its end, tracing its path through equations and theories. This act of imagining, of seeking meaning in a future we'll never see, is uniquely human. a reflection of our curiosity and resilience. We are made of atoms destined to decay, yet we ponder a universe that outlives us, finding wonder in its silence. The Boltzmann brain paradox, with its ghostly minds, mirrors our own fleeting consciousness, a reminder that even our thoughts are temporary, yet precious for their rarity. The melancholic beauty of this epoch lies in its stillness. The universe, once vibrant with galaxies, is now a canvas of nothingness, its only motion the rare flicker of quantum chance. These fluctuations, sparking brains or universes, are not beginnings but echoes, moments that fade without legacy. The cosmos, stripped of structure, is a silent witness to its own decline, its vastness a monument to what was lost. Yet there is hope in this emptiness, a possibility that new realities may emerge, each a fresh chapter in an eternal story. The scientific foundation of this era is rooted in quantum mechanics and cosmology. Boltzmann's statistical mechanics, developed in the 1800s, showed that order can arise from disorder. Given infinite time, Lindy and Villenkind's eternal inflation, proposed in the 20th century, suggests a multiverse where universes bubble endlessly. These ideas, grounded in observation and mathematics, predict a future where randomness governs, where the improbable becomes possible. The absence of time's arrow, as Carroll's work on entropy implies, completes this picture, a cosmos where change ceases, and existence becomes a statistical dream. The question of information persists as particles decay and vacuums shift. Is the universe's history every star's light, every planet's orbit preserved or lost? The black hole information paradox, where data may be encoded in radiation, finds an echo here. As the cosmos's final fluctuations carry no record, this loss, or potential preservation in quantum entanglements, raises profound questions about memory and meaning. Questions that linger in a universe without observers. The Boltzmann brain, a mind without context, underscores this, its thoughts a fleeting illusion in a reality without history. Looking to the future, this epoch is both an end and a question. The universe may drift forever, its fluctuations too rare to matter, or a new bubble might spark a cosmos with new laws. The multiverse, if real, suggests our story is one of many, each universe a fleeting experiment in an inflating landscape. This possibility, though unprovable, offers a glimmer of renewal, a chance that creation persists beyond our end. The cosmos, silent and cold, remains a stage, its emptiness a canvas for probabilities we cannot foresee. The human perspective on this future is a blend of awe and humility. We are witnesses to a brief moment, a time when stars shine and life asks questions. The universe's end, with its quantum flickers and timeless void, is a future we'll never see. Yet we trace its path, finding meaning in its strangeness. Our existence, fragile and finite, gains depth through this act, a defiance of oblivion as we ponder a cosmos that dreams in silence. The extra dimensions, though unseen, are a call to keep seeking, to imagine a reality where even nothingness holds wonder. As we conclude, we carry this narrative forward, the universe's journey, from radiant birth to quiet decay, is a human story, one of curiosity and resilience. It began with stars, faded through black holes and proton decay, and now lingers in quantum whispers, where time itself may end. The cosmos, vast and silent, is a testament to change, its truths waiting in the folds of probability. We are part of this story, our questions echoing in a universe that will outlast us, a quiet vow to keep chasing the wonder that lies beyond the edge of time.
Imagine a place where there is nothing, no light, no sound, no matter, not even the whisper of a single atom, an absolute void, a perfect emptiness, for centuries. This was our conception of space, a passive, silent stage upon which the drama of the cosmos unfolded. But what if this stage is not empty at all? What if the deepest, most profound silence is actually a roar of infinite potential? Modern physics has peeled back this veil of nothingness, and what it has revealed is one of the most unsettling and beautiful truths in all of science. The void is not empty. It is a seething, boiling ocean of energy, a phantom sea of constant creation and annihilation. This is the realm of zero-point energy, the hidden power of the universe, an invisible and inexhaustible reservoir that exists at every single point in space-time. It is the baseline hum of reality, the lowest possible energy state of the cosmos, a state which is, paradoxically, not zero. This is not a metaphysical speculation. It is a direct consequence of the laws of quantum mechanics. The uncertainty principle, first articulated by Werner Heisenberg, dictates that we can never know both the precise position and the precise momentum of a particle at the same time. This fundamental uncertainty extends to energy and time, in any field, in any system, even in a vacuum cooled to absolute zero. There must be a residual flicker of motion, an irreducible quantum jiggle. This is zero-point energy. It is the universe's insurance policy against absolute stillness, a law that decrees that nothing can ever truly be at rest. This constant vibration is not a chaotic or random noise. It is the fundamental symphony of the cosmos, a music that plays in the background of all existence. Every quantum field that makes up our reality, the electron field, the photon field, the Higgs field, is constantly vibrating, even in its ground state. These vibrations are not just a theoretical curiosity. They have real, measurable effects. They give rise to a constant stream of virtual particles, phantom entities that borrow energy from the vacuum to pop into existence for an immeasurably short time before annihilating each other and returning their borrowed energy to the void. We cannot see these particles directly, but we can see their shadows. The Casimir effect, where two uncharged metal plates in a vacuum are pushed together by an invisible force, is a direct, experimental confirmation of their existence. The pressure of the virtual particles outside the plates is greater than the pressure between them, creating a net force. The void itself can push and pull. This discovery transforms our understanding of reality. Matter is not a solid, fundamental substance, but an excitation, a ripple, a concentrated vibration in these underlying quantum fields. The space we perceive as empty is not a passive backdrop, but the very source of everything we see, the invisible foundation upon which the fabric of time, space, and matter is woven. To understand zero-point energy is to understand that what we call nothing is actually the most potent something in the universe, a sea of infinite possibility from which all of reality may have been born. The idea that energy can exist in a perfect vacuum, in what we intuitively understand as nothingness, is one of the most profound paradigm shifts in the history of science. It directly challenges our classical though common-sense understanding of the world. For centuries, our physics was built on the idea that energy is a property of things, of particles, of waves, of systems. The notion that energy could be a property of emptiness itself was unthinkable. Yet, the evidence is undeniable. The Casimir effect is not a subtle or theoretical correction. It is a measurable, physical force that can be detected in a laboratory. It is the macroscopic manifestation of the microscopic quantum foam, a direct testament to the fact that the void is alive with energy. But if this energy is real, where is it, and can we use it? This is where the mystery deepens. Zero-point energy is not like the energy stored in a battery or in a gallon of gasoline. It is a uniform, isotropic energy that pervades all of space. There is no gradient, no difference in potential that would allow us to easily extract it. To use energy, We need to create a flow from a high-energy state to a low-energy state, but zero-point energy is already the lowest possible energy state of the system. It is like trying to get water to flow out of the bottom of the ocean, and yet, the sheer amount of this energy is staggering. When physicists attempt to calculate the energy density of the quantum vacuum based on the principles of quantum field theory, they arrive at a number that is astronomically large. It is an energy density so immense that, if it were all gravitationally active in the way that normal matter and energy are, the universe would have collapsed into a black hole in the first fraction of a second of its existence. This enormous discrepancy between the theoretical calculation and the observed reality of our universe is known as the cosmological constant problem, or the vacuum catastrophe, and it is arguably the single greatest unsolved problem in all of fundamental physics. It tells us that there is something profound about the nature of vacuum energy that we do not yet understand. Perhaps there is a hidden symmetry of nature, a principle of supersymmetry, for example, where the contributions of different types of particles to the vacuum energy precisely cancel each other out, leaving only a tiny residual amount. Or perhaps our understanding of gravity itself is incomplete, and the vacuum energy does not gravitate in the same way as normal matter. Whatever the solution, the reality of this vacuum energy is not in doubt. Its most significant consequence may be playing out on the largest possible scales. The observed accelerating expansion of the universe, attributed to a mysterious dark energy, is one of the great puzzles of modern cosmology. The properties of this dark energy, a constant energy density that does not dilute as the universe expands, are remarkably similar to the properties of the vacuum energy predicted by quantum mechanics. Many cosmologists now believe that dark energy is, in fact, the macroscopic manifestation of zero-point energy, the faint, residual energy of the vacuum acting as a cosmic anti-gravity, pushing the universe apart. If this is true, then the fate of our cosmos, its ultimate journey into an ever-expanding, cold and dark future, is being dictated by the subtle, incessant quantum vibrations of empty space. The greatest mystery on the cosmological scale may have its roots in the deepest secrets of the quantum void. The allure of an infinite, ubiquitous energy source has inevitably captured the human imagination, giving rise to a subculture of invention, speculation, and science fiction centered on the idea of harnessing zero-point energy, the concept of free energy, of a device that can extract limitless power from the vacuum, has been a holy grail for inventors and theorists for decades. Patents have been filed, prototypes have been built, and countless claims have been made, often blurring the line between legitimate scientific inquiry and pseudoscience. The core idea behind many of these proposed devices is to create a localized asymmetry in the vacuum, a way to tap into the zero-point fluctuations and convert them into usable work. This is often imagined through resonant cavities or specially designed nanostructures that could, in theory, interact with the virtual particles of the vacuum, much like a windmill interacts with the wind. The Casimir effect itself is often cited as a proof of principle. If the vacuum can exert a physical force, then in principle, that force can be used to do work. A hypothetical Casimir engine might involve two plates that are cyclically brought together and pulled apart, with the attractive Casimir force doing work in one part of the cycle. However, the scientific and engineering challenges are immense. The Casimir force is incredibly weak and only becomes significant at nanometer scale separations. Building a macroscopic engine that could overcome friction and other dissipative forces to extract a net positive amount of energy remains far beyond our current technological capabilities. Furthermore, there is a deep theoretical objection rooted in the laws of thermodynamics. The second law of thermodynamics, the law of entropy, states that you cannot build a perpetual motion machine of the second kind, a machine that extracts heat from a single thermal reservoir and converts it entirely into work. The quantum vacuum, in many ways, behaves like a thermal reservoir at absolute zero. Extracting energy from it would seem to violate this fundamental principle. Most mainstream physicists argue that while zero-point energy is real, it is the ground state of the universe, and you cannot extract energy from the ground state, just as you cannot get water to flow from the lowest point in a valley. Yet, the debate continues. Some researchers argue that the quantum vacuum is not a simple thermal system and that the classical laws of thermodynamics may not apply in the same way. They propose that through clever engineering, it might be possible to create a non-equilibrium state, a way to pump the vacuum to extract its energy. These ideas remain highly speculative and are on the very fringes of accepted physics. But they speak to a deep human desire, the desire for a clean, limitless, and universally available source of power. The story of zero-point energy is, in this sense, a modern myth. It is the story of a hidden cosmic power, a secret fire that, if it could be stolen from the gods of quantum mechanics, would transform human civilization forever. While the scientific consensus remains skeptical, the dream persists. And perhaps it is a necessary dream. The quest to understand and potentially harness zero-point energy, even if it ultimately proves impossible, is pushing the boundaries of our understanding of quantum mechanics, nanotechnology, and the very nature of energy itself. It is a quest that forces us to ask fundamental questions about the relationship between energy, information, and the structure of the vacuum. And in science, sometimes the questions are more important than the answers. While the dream of harnessing zero-point energy for power remains in the realm of speculation, its real, measurable effects are already shaping our world in tangible ways. The Casimir effect, once a theoretical curiosity, has become a crucial consideration in the field of micro and nano-electromechanical systems. At the scale of microns and nanometers, where the components of tiny machines are separated by incredibly small distances, the Casimir force is no longer negligible. In fact, it can become a dominant force, causing microscopic cantilever beams to stick to their substrates, a phenomenon known as stiction. For engineers designing these tiny devices, the Casimir force is a very real and often problematic aspect of the physical world that they must account for in their designs. They must develop special coatings and surface geometries to mitigate its effects. But what was once a problem is now being seen as a potential opportunity. Researchers are now exploring ways to engineer and control the Casimir force, to turn this invisible quantum pressure into a tool. By carefully designing the shape and material properties of surfaces, it is possible to modify the spectrum of zero-point fluctuations between them, and thus to tune the Casimir force. It is possible to make it repulsive instead of attractive, or to create a Casimir torque that can cause microscopic objects to rotate. This has opened the door to a new generation of nanotechnology based on quantum engineering of the vacuum. Imagine tiny, frictionless bearings that levitate on a cushion of repulsive Casimir force, or microscopic actuators driven by the modulated pressure of the quantum vacuum. These are not science fiction, they are active areas of experimental research. The Casimir effect provides us with a direct, albeit subtle, handle on the energy of the void. It is our first, tentative step towards interacting with and manipulating the most fundamental energy field in the universe. This has profound philosophical implications. We are not just passive observers of the quantum world, we are learning to become active participants, to engineer the very fabric of emptiness. The effect is also a powerful pedagogical tool, a stark and beautiful demonstration that our intuitive, classical understanding of the world breaks down at small scales. It is a window into the quantum realm, a glimpse of a reality that is far stranger and more counterintuitive than our everyday experience would lead us to believe. The invisible force between two plates in a vacuum is a testament to the fact that the universe is governed by laws that are often hidden from our direct perception. Laws that can only be uncovered through the combined power of theoretical insight and precise experimentation. The Casimir effect is more than just a clever experiment. It is a bridge between the abstract, mathematical world of quantum field theory and the concrete, physical world of force and motion. It is where the ghost-like dance of virtual particles becomes a real, measurable pressure, a pressure that is already being incorporated into the design of our most advanced technologies, and may one day be the driving force behind the machines of the future. The quantum vacuum is not just a stage for the fleeting dance of virtual particles. It is the very foundation upon which all of matter is built. Our classical picture of matter is one of solid, inert particles, like tiny billiard balls. But quantum field theory tells us that this picture is fundamentally wrong. A fundamental particle, like an electron, is not a solid object. It is a localized, vibrating excitation of a more fundamental entity, the electron field. This field, like all quantum fields, pervades all of space-time. The particle we perceive as an electron is simply a place where this field is vibrating with a certain quantized amount of energy. When the field is not excited, when it is in its ground state, we perceive it as empty space. But even in this ground state, the field is still there, and it is still subject to the incessant zero-point fluctuations. This has profound consequences for the nature of matter. The electron is not an isolated entity. It is in constant, intimate interaction with the quantum vacuum. It is continuously emitting and reabsorbing virtual photons, the carriers of the electromagnetic force, dressing itself in a cloud of these phantom particles. This vacuum polarization effectively screens the electron's bare charge, meaning the electric charge we measure is not its true, intrinsic charge, but a value that has been modified by its interaction with the void. Similarly, the mass of a particle is not an intrinsic, fixed property. A significant portion of a particle's mass arises from its interaction with the various quantum fields that fill the vacuum. The Higgs field, for example, permeates all of space, and particles acquire mass by dragging against it. But even beyond the Higgs mechanism, the self-interaction of a particle with its own field, mediated by the virtual particles of the vacuum, contributes to its measured mass. In a very real sense, matter is bootstrapped into existence by its own interaction with the emptiness that surrounds it. This dynamic, energetic picture of matter helps to explain some of its most fundamental properties. The stability of atoms, for instance, is a quantum mechanical phenomenon that depends on the vacuum. In classical physics, an electron orbiting a nucleus should radiate away its energy and spiral into the center in a fraction of a second. The reason this does not happen is that the electron can only exist in specific quantized energy levels. These levels are determined by the electron's wave-like nature and its interaction with the electromagnetic vacuum. The lowest energy level, the ground state, is not at zero energy. It is a state of dynamic equilibrium with the zero-point fluctuations of the vacuum. The electron cannot fall any lower because there is no lower energy state available to it. The atom is stable because the void itself provides a floor, a baseline of energy below which it cannot go. This understanding has cosmological implications as well. The very first seeds of structure in the universe, the tiny density fluctuations that would later grow into galaxies and clusters of galaxies, are thought to have originated as quantum fluctuations in the vacuum during the period of cosmic inflation. The quantum foam of the early universe was stretched to astronomical scales by the rapid expansion, freezing these microscopic fluctuations into the macroscopic seeds of all the structure we see today. The universe is, in a very real sense, a macroscopic manifestation of the quantum vacuum. We live inside a frozen snapshot of the void's primordial turbulence. This completely inverts our traditional view of the relationship between matter and space. We no longer see space as a passive container for matter. Instead, we see matter as an emergent property of space, a temporary localized ripple on the surface of a deep and energetic quantum sea. The invisible foundation is the true reality. The solid world we perceive is just its fleeting expression. The relationship between zero-point energy and the laws of thermodynamics is one of the most challenging and debated topics in modern physics, highlighting a deep, unresolved tension between our understanding of the quantum world and the macroscopic world of heat and energy. The laws of thermodynamics are some of the most robust and universal principles in science. The first law, the conservation of energy, states that energy cannot be created or destroyed, only transformed. The second law, the law of entropy, states that the total disorder of a closed system always increases over time. The third law states that it is impossible to reach absolute zero temperature in a finite number of steps. Zero-point energy seems to sit uncomfortably with all of these. At first glance, the constant emergence of virtual particles from the vacuum seems to violate the first law. Where is this energy coming from? The answer, within the framework of quantum mechanics, lies in the energy-time uncertainty principle. Energy can be borrowed from the vacuum for a very short amount of time. As long as it is paid back, quickly. The virtual particles are this borrowed energy, and their brief existence and subsequent annihilation ensure that, on average, energy is conserved, so the first law holds. But in a strange, probabilistic quantum mechanical way, the real tension lies with the second and third laws. The third law states that as a system approaches absolute zero, its entropy approaches a minimum value, and all motion should cease. But zero-point energy dictates that quantum systems can never be completely at rest. Even at absolute zero, there is a residual energy and a residual quantum fluctuation. This does not necessarily contradict the third law, as the law is about the process of reaching absolute zero, but it does challenge our classical intuition about what absolute zero means. It is not a state of perfect stillness, but a state of minimum possible quantum motion. The deepest conflict is with the second law, the law of entropy. The second law is what gives time its arrow. It is why heat flows from hot to cold, why eggs break but do not unbreak, why our universe evolves from a state of order to a state of disorder. But zero-point energy seems to be a form of energy that is perfectly ordered and does not dissipate. It is a constant, coherent hum that does not seem to be subject to the relentless march of entropy. If we could extract this energy, we could theoretically build a machine that would run forever, seemingly violating the second law. Most physicists resolve this by arguing that zero-point energy is a non-thermal energy. It is not heat, and it cannot be used to do work in the same way as a hot gas. It is the ground state, and you cannot extract energy from the ground state. However, this raises a deeper question. If there is this vast reservoir of perfectly ordered entropic energy pervading the universe, why does the universe as a whole still seem to obey the second law? This tension may be a clue that our understanding of thermodynamics is incomplete. Classical thermodynamics was developed to describe systems of steam engines and gases. It may not be the final word on the thermodynamics of the quantum vacuum itself. Some theorists have proposed new frameworks, like quantum thermodynamics, that attempt to generalize the laws of heat and energy to the quantum realm. In these frameworks, concepts like entropy and temperature are redefined to account for quantum effects like entanglement and superposition. The resolution of the conflict between zero-point energy and thermodynamics is a work in progress, but it is a crucial one. It lies at the heart of our attempts to build a unified theory of physics, one that can describe both the microscopic world of quantum mechanics and the macroscopic world of our everyday experience. It is a puzzle that connects the deepest questions about the nature of energy, the arrow of time, and the ultimate fate of the universe. The puzzle of the universe's expansion is another area where zero-point energy takes center stage, acting as the prime suspect in one of cosmology's greatest mysteries. The discovery in the late 1990s that the expansion of the universe is not slowing down under the pull of gravity, but is in fact accelerating, was a profound shock to the scientific community. It implied the existence of a mysterious, repulsive force, a form of dark energy that is pushing the cosmos apart. The nature of this dark energy is completely unknown, but its properties are strangely familiar. It appears to be a form of energy that is inherent to space-time itself, with a constant energy density that does not dilute as the universe expands. This is exactly the behavior we would expect from the zero-point energy of the quantum vacuum. And so, the leading hypothesis is that dark energy and vacuum energy are one and the same. The silent, incessant hum of the quantum void is the engine driving the cosmic acceleration. This is a beautifully elegant and simple idea. It connects the largest scale phenomenon in the universe, its accelerating expansion, with the smallest scale phenomenon, the quantum fluctuations of the vacuum. It suggests that the fate of the cosmos is being written by the laws of subatomic physics. If this hypothesis is correct, then zero-point energy is not just a subtle and microscopic effect, it is the most dominant form of energy in the universe. Making up roughly 70% of the total cosmic energy budget, it is the invisible, the silent majority that is shaping the future of our reality. In this picture, the future is one of eternal expansion. As the universe grows larger, the density of matter and radiation will continue to decrease, while the density of vacuum energy remains constant. Eventually, vacuum energy will be the only significant component of the universe. Galaxies will recede from each other at ever-increasing speeds. Eventually disappearing beyond our cosmic horizon, the universe will become an increasingly cold, dark, and lonely place, a scenario known as the Big Freeze. It is a future dictated by the relentless, repulsive pressure of the void. However, as we have seen, this elegant picture is marred by the cosmological constant problem, the colossal discrepancy between the theoretical calculation of the vacuum energy and the observed value. This discrepancy is so large that many physicists believe that the simple identification of dark energy with vacuum energy must be wrong. This has led to a host of alternative theories. Perhaps dark energy is not a constant, but is a dynamic entity, a new quantum field dubbed quintessence that is slowly rolling towards its minimum energy state. In this scenario, the rate of cosmic acceleration could change over time, leading to a different ultimate fate for the universe. Or perhaps the problem lies not with the energy of the vacuum, but with our understanding of gravity. Maybe general relativity needs to be modified on cosmological scales, giving rise to an apparent acceleration without the need for any new form of energy. These are all active areas of research, and the James Webb Space Telescope is providing crucial data to help distinguish between them by precisely measuring the expansion history of the universe at different epochs. Webb can help to determine if the properties of dark energy have changed over time. The nature of the universe's expansion is one of the most fundamental questions in all of science, and at its heart lies the enigmatic nature of the void, zero-point energy. Whether it is the silent engine of cosmic acceleration or a red herring in the search for dark energy, is a concept we must grapple with to understand our cosmic destiny. It is a puzzle that connects the beginning of the universe with its end, the quantum with the cosmos, and the deepest secrets of the void with the ultimate fate of all that we know. The quantum vacuum is not just a passive energy reservoir, it is a dynamic, creative medium, a quantum foam where the very fabric of space-time is thought to be in a constant state of turmoil at the smallest possible scales. This concept, first envisioned by the physicist John Archibald Wheeler, takes the implications of the uncertainty principle to their logical extreme. If the energy of a field can fluctuate over short timescales, and if energy and mass are equivalent, then these energy fluctuations can, in principle, create tiny, fleeting curvatures in space-time. At the Planck scale, the incredibly small scale of 10 to the power of minus 35 meters, where the effects of quantum mechanics and gravity are thought to become equally important, space-time is no longer a continuous manifold. Instead, it is a roiling, chaotic foam of tiny, transient wormholes and microscopic black holes, constantly bubbling into and out of existence. In this picture, the smooth space-time of our macroscopic experience is just an average, a large-scale approximation of a much more violent and chaotic underlying reality. The quantum foam is a direct consequence of the zero-point energy of the gravitational field itself. Just like the electromagnetic field, the gravitational field has a ground state energy, and its zero-point fluctuations are what create this foamy structure. This idea has profound implications for our understanding of reality. It suggests that the concepts of distance and duration, which seem so fundamental to us, may break down at the Planck scale. The very notions of here and there, before and after, may lose their meaning in this quantum fuzziness. Time itself may not be a continuous flow, but a series of discrete probabilistic jumps, a staccato rhythm played out on the foamy stage of the quantum vacuum. This is a radical departure from the smooth, continuous spacetime of Einstein's general relativity, and it is at the heart of the search for a theory of quantum gravity, a theory that can unify the two great pillars of modern physics. But the quantum foam is not just a theoretical playground for physicists, it may have real, cosmological consequences. Some theories propose that our entire universe may have originated as a single, large quantum fluctuation in a pre-existing quantum foam, a bubble that spontaneously nucleated and then rapidly expanded in the event we call the Big Bang. In this scenario, the universe is not a unique creation, but a natural, and perhaps common, outcome of the inherent restlessness of the void. This leads to the tantalizing idea of a multiverse, a vast ensemble of bubble universes, each with its own physical laws and constants, constantly budding off from an eternally inflating quantum foam. Our universe is just one bubble among many, a fortunate fluctuation where the conditions happen to be right for the emergence of stars, galaxies, and life. This is a speculative but powerful idea, as it provides a potential explanation for the apparent fine-tuning of our own universe's physical constants. We live in a universe that is hospitable to life because we could not live in one that wasn't. We are the survivors of a cosmic lottery. The concept of the quantum foam, born from the simple idea of zero-point energy, thus leads us to the grandest and most mind-bending of all cosmological ideas. It suggests that our entire reality, with all its vastness and complexity, may be nothing more than a temporary, fortunate ripple on the surface of an infinite, eternal, and endlessly creative quantum sea. The emptiness is not just the foundation of matter, it is the womb of worlds. The creative potential of the void, its ability to birth particles and perhaps even universes, is mirrored by its potential to act as a force of anti-gravity, a concept that has long been a staple of science fiction, but which finds a tentative, theoretical grounding in the physics of zero-point energy. Our classical understanding of gravity, as described by Newton and refined by Einstein, is that it is always an attractive force. Mass and energy curve space-time, and this curvature tells other mass and energy how to move, always pulling them together. But the accelerating expansion of the universe tells us that there must be a repulsive force at play on cosmological scales, a form of cosmic anti-gravity. As we have seen, the leading candidate for this is the zero-point energy of the vacuum. The key lies in the concept of negative pressure. In normal matter, pressure is a positive quantity that acts as a source of gravitational attraction alongside its mass energy. But a field with a constant energy density, like the quantum vacuum, has a strange and counterintuitive property. Its pressure is negative, and it is equal in magnitude to its energy density. When you plug this negative pressure into Einstein's equations of general relativity, it creates a gravitational repulsion. The void, in a sense, pushes itself apart. This is the theoretical basis for the anti-gravity effect of zero-point energy. While this effect is currently only observed on the vast scales of the cosmos, it has ignited speculation about the possibility of harnessing this phenomenon for technological purposes. If we could somehow engineer a region of space to have a much higher density of vacuum energy, or if we could manipulate the properties of the vacuum itself, could we create a localized anti-gravity field? This is the dream of warp drive and other exotic propulsion systems. A hypothetical warp drive, like the one proposed by the physicist Miguel Alcubierre, would not work by accelerating a spaceship through space, but by manipulating space-time itself. It would involve creating a bubble of space-time around the ship, contracting space in front of it and expanding space behind it. The ship itself would remain stationary within this bubble, while the bubble moves through space, potentially at superluminal speeds, without violating the local speed of light limit. The energy requirements for such a device, according to the original calculations, were astronomical, requiring more energy than exists in the entire visible universe. However, more recent theoretical work has suggested that by cleverly designing the shape of the warp bubble, the energy requirements could be drastically reduced, perhaps to the mass of a large planet. The problem is that these models still require the existence of exotic matter with negative energy density. And while the Casimir effect does demonstrate a region of lower than normal vacuum energy, creating a macroscopic amount of stable, negative energy is far beyond our current capabilities and may be forbidden by the laws of physics. Despite these immense challenges, the anti-gravity potential of zero-point energy remains a tantalizing, if distant, possibility. It represents the ultimate technological ambition to graduate from being passengers on the currents of space-time to becoming its pilots. It is a dream that connects the deepest questions of quantum gravity with our most profound aspirations for a future among the stars. It is a reminder that the void is not just a source of cosmic expansion, but also a source of endless human imagination, a canvas upon which we project our hopes for a future where even the laws of gravity may one day be subject to our command. The symphony of the cosmos is played on an orchestra of quantum fields, and zero-point energy is its fundamental tuning note, the silent, ever-present hum against which all other melodies are played. This is not just a poetic metaphor, it is a deep physical truth. The properties of all the fundamental particles and forces in the universe are intimately tied to the properties of the quantum vacuum. The universe is not a collection of independent entities, but a holistic, interconnected system. And zero-point energy is the energetic medium that connects it all. Consider the very constants of nature, the charge of the electron, the strength of the fine structure constant, the mass of the Higgs boson. In our current theories, these are fundamental parameters that we must measure experimentally. We do not know why they have the values they do. But in a deeper, more complete theory, these constants may not be fundamental at all. They may be emergent properties of the vacuum, determined by the complex interplay of all the zero-point fluctuations of all the quantum fields. The values we measure may be the result of a cosmic settlement, an equilibrium state that the universe has fallen into. This is the idea behind theories like string theory, which posits that all the fundamental particles are just different vibrational modes of a single, underlying entity, a tiny, vibrating string. In this picture, the properties of the particles are determined by the way the string vibrates, which is in turn determined by the geometry of the extra, hidden dimensions of spacetime that string theory requires. The shape and size of these extra dimensions are properties of the vacuum, and thus the laws of physics themselves are a consequence of the vacuum structure. This leads to the stunning possibility that the laws of physics may not be universal in an absolute sense. If our universe is just one bubble in a multiverse, as the quantum foam concept suggests, then other bubble universes could have different vacuum states, different geometries for their extra dimensions, and therefore different physical laws. This provides a potential solution to the fine-tuning problem. The reason the constants of nature in our universe appear to be so finely tuned for the existence of life is because we live in one of the few universes where they are. In the vast cosmic symphony, there are countless dissonant, lifeless universes. We simply inhabit one of the rare, harmonious ones. This perspective transforms zero-point energy from a simple background noise into the very DNA of the cosmos, the source code that specifies the laws and constants of our reality. The silent notes of the vacuum are what determine the music of existence. The quest to understand zero-point energy is therefore not just a quest to understand a particular form of energy. It is a quest to understand the operating system of the universe. It is a search for the deepest logic of reality, the why behind the what. And as we listen more closely to the silent hum of the void, with instruments like the James Webb Space Telescope and the next generation of particle accelerators, we may begin to discern the structure of this cosmic score, to understand the principles that govern its harmony, and to perhaps, one day, learn to play a few notes of our own. The universe is a symphony, and we are the part of the symphony that has woken up and is beginning to listen to itself. It is the most profound and beautiful endeavor in all of human history. The profound interconnectedness of the quantum vacuum raises one of the most speculative, yet deeply compelling questions at the intersection of science and philosophy. Could there be a link between the zero-point energy field and the phenomenon of consciousness? This is a question that pushes the boundaries of scientific inquiry, venturing into territory that is often dismissed as mystical or pseudoscientific. And yet, the strange, non-local, and holistic nature of both the quantum vacuum and consciousness invites us to at least consider the possibility of a connection. Quantum mechanics has taught us that the universe is not a collection of separate, independent objects, but a web of interconnected probabilities. The observer effect, where the act of measuring a quantum system forces it to collapse from a state of multiple possibilities into a single, definite reality, has long suggested that consciousness may play a more active role in the universe than classical physics would allow. While most physicists interpret the observer effect as a result of the interaction of the quantum system with a macroscopic measuring device, and not necessarily with a conscious mind, a minority have long argued for a more direct role for consciousness. The theory of orchestrated objective reduction, proposed by the physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff, is one of the most well-developed of these models. It posits that consciousness arises from quantum computations occurring within microtubules, the protein skeletons of our brain's neurons. In this model, these quantum computations are not isolated. They are coupled to the zero-point fluctuations of the vacuum. the fundamental geometry of space-time. Consciousness, in this view, is a process of orchestrated collapse of the quantum wave function, a process that is not random, but is influenced by a form of Platonic information embedded in the Planck scale structure of the universe. The conscious mind, in a sense, is tapping into the fundamental information field of the cosmos, a field whose energetic manifestation is the zero-point energy. This is a highly speculative and controversial theory, and it lacks direct experimental evidence, but it is a scientifically testable one. It makes specific predictions about the quantum properties of the brain that could, in principle, be measured. But even beyond specific models like OR, the general idea of a connection between the vacuum field and consciousness resonates with many philosophical and spiritual traditions. The concept of a universal consciousness, a Brahman in Hinduism or a Tao in Taoism, a fundamental unified field of awareness from which all individual consciousness arises, has echoes in the modern physical concept of a unified quantum field that pervades all of space. Could the zero-point energy field be the physical correlate of this ancient philosophical idea? Could it be the interface between mind and matter, the medium through which intention and awareness can have a subtle but real influence on the physical world? This is a question that science is not yet equipped to answer, but it is a question that is becoming increasingly legitimate to ask. As our understanding of both the brain and the quantum vacuum deepens, we may find that the hard line we have drawn between the inner world of subjective experience and the outer world of objective reality is not as solid as we thought. Perhaps they are two sides of the same coin, two different manifestations of the same underlying information-rich and endlessly creative quantum reality. The possibility that the silent energy of the void is connected to the silent inner world of our own consciousness is a thought of breathtaking scope. It suggests that we are not just observers of the cosmic symphony, but are, in the most profound sense, an integral part of the music itself. Our thoughts, our feelings, our very awareness may be a resonance, a specific complex vibration of the same fundamental field that gives birth to stars and shapes the destiny of the universe. The technological implications of understanding and potentially manipulating the quantum vacuum are as vast as the cosmological ones. The development of quantum computers, for example, is a field that is both limited by and potentially empowered by zero-point energy. Quantum computers derive their immense processing power from their ability to harness the strange principles of the quantum world, like superposition and entanglement. A quantum bit, or qubit, can exist in a superposition of both 0 and 1 at the same time, allowing a quantum computer to explore a vast number of possibilities simultaneously. But this quantum fragility is also their Achilles' heel. Qubits are incredibly sensitive to their environment. Any stray interaction, any unwanted noise, can cause the delicate superposition to collapse, a process called decoherence, which destroys the quantum computation. And the most fundamental source of noise in the universe is the zero-point fluctuations of the quantum vacuum. The constant, random jiggle of the vacuum fields is a persistent background hiss that quantum engineers must constantly battle. They must develop sophisticated error correction codes and shielding techniques to protect their qubits from the inherent restlessness of the void. In this sense, zero-point energy is the ultimate adversary in the quest to build a large-scale, fault-tolerant quantum computer. But what if we could turn this adversary into an ally? Some theorists have proposed that it might be possible to engineer the vacuum itself, to create squeezed vacuum states where the quantum noise is reduced in one variable at the expense of increased noise in another. This could be used to create a quieter environment for qubits to operate in, pushing the limits of quantum computation. Even more speculatively, the quantum vacuum could one day become the ultimate communication medium. The phenomenon of quantum entanglement, where two particles can remain connected in such a way that a measurement on one instantly influences the other, regardless of the distance between them, seems to defy our classical notions of space and time. While it is not possible to use entanglement to send information faster than light, it does suggest a deep, non-local connectivity inherent in the fabric of reality. Some have speculated that it might be possible to modulate the vacuum state itself, to create vacuum telegraphs that could transmit information through the zero-point field. This would be a form of communication that does not involve the transmission of any particles or energy in the classical sense, but rather the propagation of a change in the state of the vacuum. Such a technology, if it were ever possible, would be truly revolutionary, offering a secure and potentially instantaneous form of communication across vast distances. The relationship between quantum information and the vacuum is a rich and complex one. It is a field where the deepest questions of fundamental physics meet the most practical challenges of next-generation technology. As we learn to build machines that can operate at the quantum level, we are also learning to interact with the universe in a new way, to speak its native language of probability, superposition, and entanglement. And in this dialogue with the quantum world, the silent, ever-present energy of the void is a constant partner, a source of both challenge and opportunity, the ultimate frontier for both our understanding and our technological ambition. The influence of the quantum vacuum is not confined to the exotic realms of quantum computing or cosmology. It leaves it subtle but detectable, fingerprints on the very properties of the light and radiation that fill our universe. Light, in the classical picture, is an electromagnetic wave that propagates through a passive, empty space. But in the quantum picture, light is a stream of photons, and the space it travels through is a dynamic, fluctuating medium. The interaction between photons and the zero-point fluctuations of the vacuum leads to a number of fascinating and subtle effects. One of these is the phenomenon of vacuum birefringence, a prediction of quantum electrodynamics that has yet to be definitively observed. In the presence of a very strong magnetic field, the vacuum itself is predicted to behave like a birefringent crystal, meaning it would have a different refractive index for light of different polarizations. A beam of unpolarized light passing through such a magnetized vacuum would emerge slightly polarized. This effect is caused by the strong magnetic field influencing the behavior of the virtual electron-positron pairs that are constantly popping in and out of the vacuum. The field aligns their spins, effectively giving the vacuum a grain or an axis that affects the light passing through it, while the effect is incredibly small. Astronomers are searching for it in the light from magnetars, the neutron stars with the strongest magnetic fields in the universe. A confirmed detection of vacuum birefringence would be a stunning confirmation of one of the most counterintuitive predictions of QED, and a direct testament to the physical reality of the virtual particles of the vacuum. Another, more subtle, effect is the potential for the vacuum to influence the speed of light itself. According to Einstein's theory of relativity, the speed of light in a vacuum is a universal constant. However, some theories of quantum gravity suggest that at the Planck scale, the foamy, fluctuating nature of spacetime could affect the propagation of light. High-energy photons, with wavelengths approaching the Planck length, might interact more strongly with the spacetime foam, causing them to travel slightly slower than low-energy photons. This would be a tiny, energy-dependent violation of Lorentz invariance, the fundamental principle of relativity that underpins all of modern physics. Astronomers are searching for this effect by looking at the arrival times of high-energy photons from distant gamma-ray bursts. If high-energy photons from a burst consistently arrive slightly later than low-energy photons from the same burst, it could be a sign of this quantum gravity effect. So far, no such effect has been detected, which places tight constraints on many of these theories. But the search continues. These are incredibly challenging measurements, pushing the limits of our observational capabilities, but they are crucial. The light that travels to us across billions of light years from the distant universe is not just a picture of the past, it is a probe, a messenger that has traveled through the quantum vacuum for eons, carrying with it subtle imprints of its journey. By carefully deciphering these imprints, by looking for tiny changes in polarization, speed, or direction, we can use the light from the cosmos to study the properties of the void itself. It is a beautiful irony that by studying the brightest objects in the universe, we can learn about the nature of its deepest darkness, and by analyzing the properties of light, we can probe the very substance of emptiness. The vast, cold, and seemingly empty cosmic voids, the great deserts of the cosmos, are being transformed by our understanding of zero-point energy from places of nothingness into laboratories of fundamental physics. These are the most pristine regions of the universe, where the density of matter is so low that the effects of the quantum vacuum are not drowned out by the noise of stars, gas, and galaxies. It is here, in the deepest silence, that we can best hope to listen to the hum of the void. The existence of these voids is a natural consequence of the gravitational instability that drives the formation of the cosmic web. As gravity pulls matter together to form the great filaments and clusters, it necessarily leaves behind these vast, underdense regions. But the properties of these voids, their size, their shape, their degree of emptiness are sensitive probes of the underlying cosmology. For instance, the nature of dark energy has a direct impact on the evolution of voids. A universe with a strong, repulsive dark energy will have voids that grow larger and emptier over time, as the cosmic acceleration pushes matter out of them more efficiently. By studying the statistics of voids at different cosmic epochs, astronomers can place constraints on the properties of dark energy, providing a powerful, independent check on the measurements from supernovae and the CMB. Webb is a powerful tool for this kind of void cosmology. Its sensitivity allows it to detect the faint, isolated dwarf galaxies that live within the voids, providing the crucial tracers needed to map their structure and evolution. But voids are not just tracers of dark energy, they may also be laboratories for testing our understanding of gravity. Some modified gravity theories, proposed as alternatives to dark energy, predict that the law of gravity should be different in low-density environments. In these theories, the gravitational force can be screened in high-density regions like our solar system, which is why we do not see any deviation from general relativity locally. But in the low-density environment of a cosmic void, this screening mechanism would be less effective, and deviations from Einstein's gravity might become apparent. By studying the motions of galaxies on the edges of voids and the weak gravitational lensing of background light by the sparse matter within them, we can test these modified gravity theories with unprecedented precision. The voids, in this sense, become the perfect place to look for a breakdown of our standard laws of physics. Finally, the voids are the best place to search for the subtle, large-scale signatures of the early universe. The faint temperature fluctuations in the cosmic microwave background are thought to be the seeds of all structure, but they have been processed and modified over billions of years of gravitational evolution. The voids, however, have evolved much less than the dense regions. They are, in a sense, a more direct, less processed window into the primordial universe. By studying the subtle patterns in the distribution of the few galaxies that do exist within voids, we may be able to detect the faint, non-Gaussian signatures predicted by some models of cosmic inflation, or even the aforementioned cosmic bruise that could signal a collision with another universe. The great cosmic voids are no longer the boring, empty spaces on the cosmic map. They are a new frontier, rich with information, a place where the secrets of dark energy, gravity, and the very beginning of the universe may be waiting to be discovered. They are a testament to the fact that in cosmology, as in so much of science, there is often as much to be learned from the absence of things as there is from their presence. The dynamic, energetic nature of the quantum vacuum, as described by zero-point energy, provides a new and powerful lens through which to view the very origin of the universe, offering a potential path to answering the ultimate cosmological question: why is there something rather than nothing? The traditional Big Bang model, while remarkably successful, has a fundamental limitation. It describes the evolution of the universe from a hot, dense state, but it cannot explain the origin of that state itself. The initial singularity is a point where the laws of physics break down, a moment of creation that lies outside the realm of scientific explanation. But the physics of the quantum vacuum allows for a different kind of beginning, a beginning that is not a violation of physical law, but a consequence of it. This is the concept of the universe from nothing, a concept that is often misunderstood. The nothing in this context is not the absolute, philosophical nothingness of non-existence. It is the quantum vacuum, a state devoid of matter and radiation, but rich with potential energy and subject to quantum fluctuations. In this picture, our universe could have been born from a spontaneous quantum tunneling event, just as a quantum particle can tunnel through an energy barrier that it classically could not overcome. The universe itself could have tunneled into existence from a state of nothing to a state of something. This idea was most famously developed by physicists like Alexander Vilenkin and Stephen Hawking in his no-boundary proposal. In this model, the universe did not have a beginning in time because time itself was created in the tunneling event. The question, what came before the Big Bang, becomes meaningless. Just as it is meaningless to ask what is north of the North Pole, the universe did not arise in time, it arose with time. It is a self-contained, self-creating system, born from the inherent quantum restlessness of the void. This is a profoundly beautiful and self-consistent picture. It removes the need for a supernatural creator or a first cause that lies outside of science. The universe, in this view, is the ultimate free lunch. The total energy of the universe is thought to be exactly zero. The positive energy of matter and radiation is perfectly balanced by the negative gravitational potential energy. Since the creation of a system with zero total energy does not violate the law of conservation of energy, the universe can, in principle, pop into existence from the vacuum without any external cause. The zero-point energy of the vacuum is the crucial ingredient that makes this possible. It is the energetic froth from which a zero-energy universe can spontaneously nucleate. This concept also leads naturally to the idea of a multiverse. If our universe can be created by a quantum fluctuation, there is no reason to think it was a unique event. The quantum vacuum is a fertile ground, and universes may be constantly bubbling into existence, each with its own set of physical laws and constants, determined by the specifics of the tunneling event. This provides an elegant, if unprovable, solution to the fine-tuning problem. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves on a planet that is hospitable to life. It is a selection effect. We could not have evolved to ask the question in any of the other, far more numerous, inhospitable universes. The origin of the universe is perhaps the deepest and most profound question that science can address. And while we may never have a definitive, final answer, the physics of zero-point energy has, for the first time, provided us with a plausible scientific framework for understanding how a universe like ours could come to be. It suggests that existence is not a strange and improbable exception, but perhaps the natural, and even inevitable, consequence of the laws of quantum mechanics playing out on the canvas of the void. Something exists because nothing, in the quantum sense, is fundamentally unstable. The creative, energetic, and foundational nature of the quantum vacuum, as described by the concept of zero-point energy, represents one of the most significant and revolutionary shifts in our understanding of reality since the birth of modern science. It is a concept that has taken us from a view of a static, passive, and empty space to a vision of a dynamic, creative, and endlessly energetic quantum sea. This is not just a change in a scientific model, it is a change in our fundamental relationship with the cosmos. We have learned that the solid world we perceive with our senses is a fleeting though emergent illusion, a temporary ripple on the surface of a much deeper but invisible reality. The particles that make up our bodies are not solid, immutable things, but localized vibrations of fields that extend throughout the entire universe. We are, in the most literal sense, woven from the fabric of the void. The forces that govern our world, from the light that allows us to see to the gravity that holds us to the earth, are mediated by the constant, fleeting dance of virtual particles born from the vacuum's energy. The very stability of the atoms that make us up is a delicate equilibrium with the zero-point fluctuations of the surrounding space. The grand architecture of the cosmos, the vast web of galaxies and voids, is a macroscopic fossil of the quantum turbulence of the early universe. The fate of our universe, its journey into an accelerating and perhaps eternal expansion, is being driven by the mysterious, repulsive pressure of the void itself, and the very origin of our reality. The event we call the Big Bang may have been a spontaneous quantum leap from the potential rich nothingness of the vacuum into the manifest existence we now inhabit. This is a worldview that is both profoundly humbling and deeply empowering. It is humbling because it reveals the severe limitations of our own perception and the vastness of our ignorance. 95% of the universe is made of dark matter and dark energy, mysterious entities whose nature we do not yet understand, but which are likely tied to the properties of the vacuum. Our entire existence is a fragile 5% exception in a vast, dark, and invisible cosmos. But it is also empowering because it is a testament to the incredible power of the human mind. Through the abstract language of mathematics and the rigorous process of scientific inquiry, we have been able to deduce the existence of this hidden reality, to measure its effects, and to begin to understand its profound implications. We have built tools, like the James Webb Space Telescope, that allow us to peer into the void and listen to its secrets. The quest to understand zero-point energy is a journey to the very heart of reality. It is a quest that connects the smallest scales with the largest, the beginning of time with its end, and the most abstract theories of physics with the most tangible questions of our own existence. It is a journey that is far from over. The great puzzles, like the cosmological constant problem and the nature of dark energy, remain unsolved. But in grappling with these puzzles, we are pushing the boundaries of human knowledge and expanding our vision of what is possible. The silent, invisible energy of the void is the ultimate scientific frontier. A frontier that promises to yield new discoveries, new technologies, and a new, more profound understanding of our place in the cosmic symphony. The universe is stranger, more beautiful, and more deeply interconnected than we ever dreamed. And the key to its deepest secrets may lie where we least expected it, in the perfect, potent, and creative power of its own emptiness.